Introduction of the Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Larry Wilson. The Science History of the Universe, Volume 1, edited by Francis Rolt-Wheeler. Astronomy. Introduction. In the present volume there have been covered in a comprehensive and popular manner the various departments of astronomy. Owing to its treatment in a definitely historical and descriptive manner, however, it may be possible to supplement the general review by a few brief statements of some of the results and problems that confront us in the actual work of the observational astronomy of today. There is frequently brought before the astronomer the fact that certain subjects that were apparently exhausted have proved through the more advanced methods of today, or perhaps by chance, to be veritable mines of discovery, richer by far than had been anticipated in all the previous investigations. A remarkable illustration of this fact is the splendid work of Professor Hale at the Solar Observatory of the Carnegie Institution at Mount Wilson, California. The Sun had almost been relegated to that limbo from which nothing new can ever come. With the exception of Hale's development of the spectroheliograph, which made possible the continuous photographic study of the surface of the Sun and of the solar prominences, but little advance had been made in solar research for a very long period of time. Even with the new instrument, the work seemed to be confined to the photography of the prominences and a few other features of the Sun that were already observable visually with the spectroscope. Before this, the Sun was somewhat of a curiosity, and but little new information was had concerning it. It only became really interesting when a total eclipse was imminent, at which time the corona could be seen and studied. The spectroheliograph was the first great step in the study of the Sun. Even though this made possible a continuous photographic record of the prominences and kindred features, it could not record the more attenuated and delicate corona. Indeed, we seem today as far as ever from any sight of this mysterious object without the aid of the friendly Moon, which for a few minutes at long intervals hides the Sun and gives us our only view of the corona. But the great work done by Professor Hale and his associates at Mount Wilson, which was foreshadowed by his work at Yerkes Observatory, in the discovery of the solar vortices and magnetic fields of sunspots, has revolutionized the study of that body and opened up new fields of investigation in this direction that are almost unlimited. Mr. Abbott of the Smithsonian Institution has also established a permanent station at Mount Wilson for the investigation of the solar constant and a general study of the heat of the Sun. The solar investigations, therefore, that are going on at Mount Wilson are among the most important that have ever been undertaken. They are not only of the highest interest, but may ultimately lead to important results bearing upon the commercial life of the world by revealing to us some possible means of forecasting conditions upon the Earth. Any vagaries in the Sun must have more or less direct influence on the conditions of the Earth, which owes its very throb of life to the mighty influence of the Sun. Much of the ordinary spectroscopic work may be said to be in its infancy because of the vast fields of research that are open to it. It is already laying the foundation for a very accurate determination of the distance of the visible binary stars where both stars can be observed with the spectroscope, an accuracy that can never be obtained by the ordinary methods of parallax work. Already this has given results of precision in the case of Alpha Centauri, whose distance has been determined by Professor Wright of the Lick Observatory from spectroscopic observations combined with the known orbit of the star. Time, however, is an element in this work, and after a sufficiently long interval a valuable harvest of knowledge of star distances will result. The spectroscopic material for such investigations is being specially obtained by Professor Frost and his associates at the Yerkes Observatory, as well as by others elsewhere, where spectrograms of the various visual binaries that are bright enough to give a measurable spectrum are being carefully and accurately accumulated. A possible improvement of the spectroscope, whereby a larger percentage of the light can be utilized, will make possible the extension of this class of work, for at least 90% of the available light cannot at present be utilized. If this can be done, the efficiency of the spectroscope will be vastly increased and a great number of objects at present beyond the reach of accurate spectroscopic study will be investigated and their nature and physical conditions become known. A step in this direction is the intended erection on Mount Wilson of a reflecting telescope 100 inches in diameter. The great light-grasping power of this instrument will enable much fainter objects to be studied than can be observed with the present means. Only a few years ago our knowledge of comets seemed to be satisfactory. What we could see with the naked eye or with the telescope apparently readily agreed with certain theories that were formulated to explain them. The tails of various comets were sorted out and assigned to different classes. This one was a hydrocarbon tail, and that a hydrogen tail, etc. The spectroscope had shown that comets in general consisted of some form of hydrocarbon gas, such as cyanogen. Such gas or gases are evidently mixed up with the minutely divided matter which is disrupted and expelled from the comet's head and thrown out backward from the comet away from the Sun. This was shown later by the experiments of Lebedew, Nichols, and Hull to be due to the pressure of the Sun's light upon the smaller particles of the comet, which drove them away into space with increasing velocity to form the tail. The simple phenomena thus seen by the eye were rather easy of explanation. Photography, however, has revealed such a mass of strange phenomena in these bodies that the theories which seemed so satisfactory before are now seriously questioned, and some of them appear to be entirely inadequate to explain some of the phenomena shown by the photographic plates. But little indication of many of the most extraordinary changes and peculiarities of comets' tails is seen by the eye. In part this is due to the fact that much of the light of a comet is of a nature that has but little effect on the human eye, though it is peculiarly strong in its action on the photographic plate. The first of these bodies to exhibit these peculiarities was Comet 4, 1893, Brooks. Some of the phenomena of its tail, as revealed by the photographs, appeared to defy the ordinary theories and seemed to show that an influence outside that of the direct action of the Sun upon the comet had manifested itself in the distortion and breaking of the tail. The scarcity of active comets in the succeeding years left this question in abeyance. Comet C, 1903, Borrelly, however, gave us much information as to the actual velocity of the outgoing particles of the tail, some of which receded from the comet at the rate of 29 miles a second. This object also quite clearly showed that a seat of force of great activity existed in the comet itself, which enabled it to shoot out streams of matter at large angles to the main direction of the tail, which were apparently not bent or affected by the pressure of the Sun's light. The phenomena of Comet 4, 1893, were repeated in Comet C, 1908, Morehouse. But a great amount of the new phenomena was also shown by the last body, which demands still greater changes in our ideas of comets and their tails. This object is so recent and its phenomena so startling that astronomers have not yet had time to thoroughly discuss the vast amount of material that exists for its study. Briefly, added to the already known rapid changes in the tail of a comet, this object exhibited the most extraordinary freaks. Tails were repeatedly formed and discarded to drift out bodily in space until they finally melted away. In several cases the tail was twisted or corkscrew shaped, as if it had gone out in a more or less spiral form. Areas of material connected with the tail would become visible at some distance from the head, where apparently no supply had reached it from the nucleus. Several times the matter of the tail was accelerated perpendicularly to its length. At one time the entire tail was thrown forward and violently curved perpendicularly to the radius vector in the general direction of the sweep of the tail through space. This peculiarity is opposed to the laws of gravitation. There is no known cause for this freak of the tail. Evidently we have here, and in many other of the phenomena of this body, some unknown influence at work in the planetary spaces. What this is one of the great problems for the future to solve. It has been suggested that many of the unaccountable phenomena of this comet are electrical and can be attributed to the same influence that produces our magnetic storms and auroras on Earth, and these are believed to be due to abnormal disturbances on the Sun. It is to be hoped that the present return of Halley's comet will add much to a solution of this problem. The study of the dark or apparently vacant regions of the sky, especially in the Milky Way, is of paramount importance. The photographic plate has shown that the dark regions, the so-called coal sacks, are generally connected with masses of nebulosity or gaseous matter. These are especially remarkable in the regions of the stars Theta Ophiuchi and Rho Ophiuchi. In the latter case we find a magnificent nebula in a rich region of the Milky Way, occupying a hole that is apparently devoid of stars. Some astronomers have attributed the general absence of stars here to absorbing matter, to an opacity and partial dying out of the nebula that cuts off the light of the stars which are beyond it. What these apparent vacant regions really are is, therefore, an unsolved problem at present. Some of them are evidently due to the thinning out and actual absence of stars in those parts of the sky. But the others, which are connected with nebulosities, seemingly must have some other explanation. One fact that appears to be brought out by the great nebula of Rho Ophiuchi is that the groundwork of the Milky Way in this region, and by inference elsewhere, may be made up of stars actually much smaller than the average of those seen in the general sky. If this were so, it would materially change our ideas of the Milky Way. This supposition comes from the fact that the great nebula is connected with some of the brighter stars in this region, while at the same time there is apparently evidence that it is connected with the faint stars that form the groundwork of the Milky Way here. If, however, the dark regions about and near the nebula are due to the absorption of light by an opacity of the nebula, the supposition as to the relative sizes would not hold, for the nebula in that case might be very much nearer to us than the Milky Way. It will be evident that an understanding of the nature of the dark regions of the Milky Way is of the utmost importance to a proper knowledge of our stellar universe. The great nebulous regions of the sky that photography has revealed to us are intimately connected with the Milky Way. They cover very large regions of the heavens and must be almost inconceivably great. In no case has it been possible to determine the exact dimensions of these wonderful objects, because we do not know their distances. It is possible, however, by assumptions that are justified by facts, to arrive at some idea of their minimum extent. If they are no further away than the nearest fixed stars, and from their evident connection with certain stars we know that they must be much further away, we can form some idea of their vastness. Our own sun, if removed to the distance of the nearest fixed stars, would present an apparent diameter of about the 100th part of a second arc. Its known diameter is something like 1,000,000 miles, accurately 867,000 miles. Some of these nebulous regions are many degrees in diameter. The one connected with the Pleiades is 10 degrees in diameter. It is certainly connected with the cluster whose distance is much beyond the nearest fixed stars. From this it will be readily seen that this great nebulous region must be at least some 4,000,000 times greater in diameter than our sun, or over 100,000 times greater than the entire diameter of our known solar system. These are figures that appear to be appallingly great, but they are only relatively so, and only shock us because the facts are new and we are not used to them. What is the ultimate function of these enormous masses of gaseous matter that we find lying in space? Are we sure that they are the primitive matter from which worlds and systems are finally to be evolved? These, very briefly, are a few of the problems that we encounter in astronomy as developed by the subtle means of research in use at the present time. E. E. Barnard. End of introduction.
Section 1 of The Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Avai in July 2015. The Science History of the Universe, Volume 1, edited by Francis Rolt-Wheeler. Astronomy. Chapter 1. The Evolution of Astronomical Ideas. Herbert Spencer has stated that evolution is a change from the indefinite to the definite, from the incoherent to the coherent. If any proof of that doctrine were required, it would assuredly be found in the development of astronomical conceptions. In this chapter an attempt will be made to outline in a general way the manner in which the present theories were evolved from the mysticism of folklore and religion. Some of the matter herein presented is drawn from Arrhenius' Die Vorstellung vom Weltgebäude im Wandel der Zeiten. The astronomical beliefs of prehistoric men were no doubt similar to those entertained by the Eskimo of the Arctic regions and the untutored tribes of Argentine Republic, South Africa, and Australia, tribes who, living only for the day, concern themselves but little with tomorrow and yesterday, and care nothing about the universe. Somewhat more cultured than these Eskimo and South American and South African tribes are primitive nations who have endeavored to account for the origin of the earth and the heavens by anthropomorphic theories. The universe must have been created by some personal being who had at his disposal something to mold. The idea that the universe was made out of nothing is a philosophical assumption which was introduced by the highly cultured philosophers of the East. The something out of which the universe was created is usually regarded as water, an element which to the eye at least is perfectly homogeneous, shapeless, and chaotic. That the fertilizing mud was deposited by floods must have attracted the attention of ancient primitive races, for which reason they may have assumed that all the earth was slowly and gradually deposited from water. Thus we find that Thales, 550 B.C., argued that all things were created from water. Yet other substances were assumed as primordial matter, and later Anaximenes of Miletus, who also flourished in the 6th century, called the generative principle of things air or breath, while Heraclitus, who flourished at Ephesus near the end of the 6th century, believed that all bodies were transformation of one and the same element, which he called fire. The belief that primordial water is the origin of all things was deeply rooted in Asiatic races, for it occurs over and over again in many creation myths, among others in the Chaldean and in the Hebrew. Instead of water, we sometimes find that an egg may be taken as the primal unit, no doubt because every organism springs from an apparently lifeless seed. Thus we find that the egg plays a most important part in the creation myths of the Japanese, as well as in narratives from India, China, Polynesia, Finland, Egypt, and Phoenicia. In many of these creation myths, of which I. Riem has collected no fewer than 68, more or less independent of one another, deluges are prominent features. In nearly all of them it is supposed that after the water subsided the land was exposed, fertilized, and made to bring forth. All of these creation myths are interwoven and interconnected with religious belief. To the savage mind everything that moves is endowed with a spirit. Accordingly, primitive man endeavors to propitiate the spirit by magic, knowledge of which art is given only to the medicine man or to the priest. In a certain sense, therefore, magic is the precursor of natural science, and the myths and lore upon which the practice of magic is based are remotely antecedent to our scientific theories. According to Andrew Lang, myths are based as much upon primitive science, resting upon superstition, as upon primitive religious conceptions. In Maspero's Histoire ancienne des peuples de l'Orient classique, we find an account of the Chaldean conception of the universe. Surrounded on all sides by the ocean, the earth rises in the middle like a high mountain whose summit is covered with snow from which the Euphrates springs. The earth is encircled by a high wall, and the abyss between the earth and the wall is filled by the ocean. Beyond it is the abode of the immortals. The wall supports the vault of the firmament, shaped by Marduk, the sun god, out of a hard metal, which shines in the daytime, but which at night is like a blue bell set with stars. In the morning the sun enters the vault by an eastern entrance, and at night makes its exit by a western outlet. Marduk arranged the year according to the course of the sun, and divided it into 12 months, each of which counted 3 periods of 10 days. The year, therefore, numbered 360 days. Every 6th year a special year was intercalated, so that the year had on an average 365 days. As the lives of the Chaldeans were to a high degree influenced by a change in the seasons, they laid great stress upon division of time. In the beginning they probably based their chronology upon the movements of the moon, like many another race. Soon they recognized that the sun exerted a stronger influence, and accordingly they introduced the solar year, whose divisions they ascribed to Marduk. The stars were observed because their positions determined the seasons. Since the seasons govern organic life, a pernicious belief in the influence of the stars took root, a belief which prevailed for 20 centuries, and which crippled the advance of science up to the time of Galileo. Diodorus Siculus, a contemporary of Julius Caesar, describes this astrology in the following words, as given in a translation by Philemon Holland, 1700. Quote, "Therefore, from a long observation of the stars, and an exact knowledge of the motions and influences of every one of them, wherein they excel all others, they (the Chaldean astrologers) foretell many things that are to come to pass. They say that the 5 stars, which some call planets, but they interpreters, are most worthy of consideration, both for their motions and their remarkable influences, especially that which the Grecians call Saturn. The brightest of them all, and which often portends many and great events, they call Sol. The other 4 they name Mars, Venus, Mercury, and Jupiter, with our own country astrologers. They give the name of interpreters to these stars, because these only by a peculiar motion do portend things to come, and instead of Jupiters do declare to men beforehand the good will of the gods, whereas the other stars, not being of the number of the planets, have a constant ordinary motion. Future events, they say, are pointed at sometimes by their rising, and sometimes by their setting, and at other times by their color, as may be experienced by those that will diligently observe it. sometimes for showing hurricanes, at other times tempestuous rains, and then again exceeding droughts. By these, they say, are often portended the appearance of comets, eclipses of the sun and moon, earthquakes, and all other the various changes and remarkable effects in the air, boding good and bad, not only to nations in general, but to kings and private persons in particular. Under the course of these planets, they say, are 30 stars, which they call counselling gods, half of whom observe what is done under the earth, and the other half take notice of the actions of man upon the earth, and what is transacted in the heavens. Once every 10 days' space, they say, one of the highest order of these stars descends to them that are of the lowest, like a messenger sent from them above, and then again another ascends from those below to them above, and that this is their constant natural motion to continue forever. The chief of these gods, they say, are 12 in number, to each of which they attribute a month, and one sign of the 12th in the zodiac. Through these 12 signs the sun, moon, and the other 5 planets run their course. End quote. The Chaldean priests developed a most perfect astrology. They mapped out the positions of the stars for every day with such care that they could tell their true positions for some time in advance. The different stars either represented deities or were directly identified with them. If, therefore, a Chaldean king wished to know which gods ruled over his destiny, he consulted the priests as to the position of the stars on his birthday, and was informed of the chief events of his career. This Chaldean belief that the celestial bodies were gods transformed astronomy into a religion. Hence astronomical theories were promulgated only by the ruling priest caste. To doubt the tenets of that caste was to expose oneself to merciless persecution, an Oriental trait that passed over to the nations of classic antiquity and to the semi-barbarous nations of the Middle Ages. The Jews appropriated the Chaldean conception of the universe, but modified it, so that it was transformed from a polytheistic to a monotheistic conception. No doubt the Chaldaic accounts of the beginning of the world influenced Egyptian thought. According to Maspero, the Egyptians believed that matter without form was shaped by a deity, always a different person in different parts of the land, and by different methods, into the world as we see it. The classic nations borrowed much of Egyptian civilization, and with it Egyptian religion and science. For the Greek creation myth, like all the others, assumes that chaos once existed, and that out of it Ga, the mother of all things, and her son, Uranos, the god of heaven, were created. The Greek cosmogony was adopted by the Romans without noteworthy development. Hence it is that Ovid wrote on the origin of the universe much as Hesiod had done 700 years before. In that long interval of 7 centuries the study of nature had advanced but little. Indeed, it was not until the invention of the telescope that astronomy was lifted entirely out of the hands of the priesthood and placed upon a sure scientific footing. Before the invention of the telescope, therefore, astronomy appears merely in the garb of a myth. At its best it was metaphysical. The rudiments of astronomical science are to be found in the efforts of the Chaldeans, Egyptians, and Greeks to devise calendars and to mark time. That effort necessitated a study of the motions of the celestial bodies. Moreover, exigencies of husbandry rendered necessary some method of keeping track of the seasons, so that seed time and harvest could be ascertained. The regular occurrence of such events as the Nile flood made requisite suitable preparations. Hence the early Egyptians so built their temples that they might know the time of the summer solstice, and hence the time when the flood might be expected. This was a matter of practical importance, not merely connected with religion or priestcraft, but on which the lives and the happiness of the people of Egypt depended, and might be compared with the modern time observations made at the great national observatories. The observation of the stars was carried on with at least this object in view, and gradually with the development of civilization, time reckoning from the stars became an important consideration closely connected with the lives of the people. With the study of the stars for such a purpose, naturally an amount of information as to their positions and motions was accumulated, and for centuries the practical side of astronomy was the study of the position of the stars and the motion of the planets. The astrology of the Chaldeans spreading westward increased rather than diminished the interest in the stars, for not only was the connection of the planets with natural phenomena and the mere reckoning of time studied, but the mystical element involving prophecy of future events attracted attention. In other words, astrology was a pseudo-science, for which reason it is difficult to estimate its benefits or to exaggerate its evil. In its scientific aspect it involved the observation and record of the position of the heavenly bodies with all the exactness that the mathematical and observational methods of the time could achieve. It enabled the motions of the planets to be studied, as well as the positions of the fixed stars and the course of the sun as it passed through them. But, on the other hand, when the interpretation of the appearance of the skies was involved, superstition and poetic fancy had full sway, in which no doubt certain elements of self-interest and deception on the part of the priests or astrologers were not lacking. Hence these men did not study the sky to interpret phenomena on a scientific basis. Confined in the narrow limits of superstition, they not only made no progress, but actually held back astronomy as they did other sciences. That the work of the astrologer was mysterious there can be no doubt, and as no reason was assigned for the movement of the planets or the position of the stars, it was a natural assumption on the part of the people that some supernatural agency was at work, which also was connected with their lives and their future. With the beginning of the development of scientific astronomical theory proper, the power and position of the astrologers began to wane, slowly, it is true, for when Tycho Brahe was invited to deliver lectures on astronomy at the University of Copenhagen, the first dealt very largely with astrology. Cardan and Kepler among the distinguished astronomers of the Middle Ages, Roger Bacon, Burton, and Sir Thomas Browne were among the men of mind who were interested, at least in part, in the teachings of the underlying basis of the cult. As explanations of the motions of the heavenly bodies on a rational basis were forthcoming, the doom of the astrologer, so far as participation in the scientific creed of the day was concerned, was sealed. If there was a natural explanation that could be accepted, how could supernatural influences condition the movements of the planets or the positions of the stars? If then these movements were natural and made in obedience to natural laws, how could they affect the future course of life and future occurrences that obviously had no connection with natural phenomena? The law of gravitation, which explained the solar system and the movement of the planets, corroborated this view, and left only the comets as striking natural phenomena which could not be explained in a way that the popular mind could grasp. With the rise of learning and the growth of observation, the explanations of natural phenomena by astronomers secured acceptance by the people. Finally, when Halley's prediction of the return of his comet, first made in 1705, was verified in 1758, the reign of natural law in the world of the heavens became an accepted fact, from which only the ignorant or superstitious could dissent. Distinctly different and apart from astrological influence was the work of Copernicus, whose researches mark the beginning of the new and philosophical science of astronomy, in which the element of mysticism was gradually displaced and observation and reasoning were depended on. Copernicus, as will be seen when the development of theories of the solar system is considered in an early chapter, returned to many of the fundamental ideas of Pythagoras and the early Greek philosophers, especially that the sun was the center of the universe. He was a thoughtful student not only of Greek philosophy, but of the work of such later astronomers as Ptolemy and his successors, so that when he announced a theory of the solar system in which the Earth and other planets revolved around the sun as a center, it was based upon the fullest knowledge of previous reasoning and theory. Nevertheless, he was casting to one side the tradition and the science of the day as it was then understood, and presenting what was a conception of the heavenly world no less daring than original. His theory was a natural outcome of the revival of learning in the Renaissance, foreshadowed by the work of such men as Leonardo da Vinci and others in whom the scientific spark had been awakened. With Copernicus, the evolution of his heliocentric theory was a matter of scientific reasoning rather than of direct observation. But it marked the beginning of a series of epoch-making discoveries presented in a clear and positive form, so that the theory of the revolution of the planets around the sun became one of the fundamental canons of astronomy. Thus, as will appear in the course of our history, the Copernican theory in which the revolution of the planets around the sun is made clear, Kepler's theory of planetary motion in which laws are stated to account for this motion, and finally Newton's announcement of the great universal law of gravitation are the foundation stones on which modern astronomical science firmly rests. The invention of the telescope established the similarity in the bodies of the solar system and revealed facts that previously had been hidden from observers of the heavens. Indeed, with the invention of the telescope and the growth of mathematical science, there began an era of descriptional astronomy in which exact observation was combined with careful computation and mathematical analysis, an era which continued into the 19th century with undiminished vigor. Brilliant discoveries were made possible by improved and powerful instruments, accompanied by theoretical work of even greater value. In the middle of the 19th century, new instruments were put at the command of the scientist, which had a remarkable effect in extending the boundaries of the science. The telescope had facilitated merely the observation of the stars. The spectroscope, on the other hand, enabled the astronomer to ascertain their composition. With the application of the spectroscope to astronomy began the welding of physics and chemistry with astronomy, and the birth of that modern science of astrophysics, which has afforded data for the study of the serious problems connected with the evolution of the universe. From the soothsaying stargazer of Chaldean times to the modern astrophysicist who works in a laboratory as well as in an observatory, we have a development that is responsible for the aggregation of knowledge, which we now possess of the vast universe with its suns, planets, stars, and nebulae. The spectra of distant celestial bodies recorded on the photographic plate by the spectrographs of large telescopes are now studied in comparison with the spectra of terrestrial substances produced in the physical laboratory. Not only the nature and composition of the stars can be ascertained, but also their motion in space, which are beyond the range of any telescope. The new astronomy has become on its astrophysical side almost an experimental science, with the methods and accuracy of the chemical or physical laboratory. It is from this modern astronomy, with its breadth and resourcefulness, that modern science looks not only for advances in its own particular field, but in the broader and ever interesting problems of cosmogony as concerned in the evolution of the stars and other bodies making up the universe. End of section 1. Section 2 of The Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Avai in July 2015. The Science History of the Universe, Volume 1, edited by Francis Rolt-Wheeler. Astronomy. Chapter 2. The Evolution of Astronomical Methods of Observation, Part 1. The history of astronomical observation is the history of man's attempt to bring the stars nearer to him. His own senses are so feeble and so very subject to error that he has been constrained to devise subtle artificial senses which take the place of eyes and hands. Thus, early he invented position finders, which enabled him to determine with more or less precision a star's direction or position at a given time, and not merely to guess at their position; great eyes, called telescopes, that see what his eyes can never see, and also determine positions with greater accuracy; wonderful spectroscopes, that analyze a star's composition as nicely as if it were a stone picked up in the road; and photographic devices that reveal secrets of star structure that otherwise would never be disclosed by his unaided senses. For determining the position of the heavenly bodies the instruments used have always been comparatively simple. All are based on certain rudimentary geometric principles. As geometry was a science fairly well developed among the ancients, it is not difficult to realize that they had various means of measuring angles, both vertical and horizontal. In most ancient cases, however, the observers have failed to hand down their methods, merely recording the results without indicating the circumstances in which they were obtained, so that it is impossible to discuss the values of the observations and correct them in the light of recent discoveries. It is evident that the instruments of the ancients were simple, but their precise nature is altogether uncertain. The earliest astronomical observations of which there is record were made by the Chinese. The Shu King, the oldest known scientific work, states that 2000 years before the present era the Chinese determined the seasons, that is to say, the positions of the sun at the equinoxes and solstices, by means of 4 stars which have since been identified and found to be so suitable that a modern astronomer could not have made a better choice. The Chinese also determined, 1100 years before the present era, the obliquity of the ecliptic, which they found equal to 23 degrees 54 minutes. The obliquity, which varies, is now 23 degrees 37 minutes, and calculation shows that at the epoch of the Chinese observations it must have been 23 degrees 51 minutes. Hence the error of the Chinese determination was only 3 minutes of arc. Among the few astronomical values which have remained constant during the history of man are the times of revolution of the planets. The Hindus determined the revolution of Mercury with an error of 4/10,000 of a day. For Venus the error was 25/10,000 of a day, for Mars 3/1000 of a day. In the case of Jupiter the error amounts to 1/4 of a day, but it is to be remembered that the period of revolution of this planet exceeds 11 years, so that the same observer could not observe many returns of the planet to the same point of its orbit. This comment applies with still greater force to Saturn, the revolution of which occupies 29 years. Hence it is not astonishing that in this case the Hindus were 6 days in error. Among the ancient Greeks is a measurement of a terrestrial meridian made about 200 B.C. by Eratosthenes, 276 BC to 195 or 196 BC, who found the circumference of the Earth equal to 250,000 stadia by measuring the angular distance of the Sun from the zenith at the summer solstice both at Alexandria and at Syene in Upper Egypt, by means of the length of shadow cast by a vertical pillar at noon at each place. According to the researches of Tannery, the stadium as an astronomical unit equals 157.5 meters, 516.7 feet, which gives for the Earth's circumference a length of 39,690 kilometers, 24,662 miles, instead of 40,000 kilometers, 24,855 miles, as we know it. Here the precision is remarkable, especially when it is remembered that the measurement was effected by counting the paces contained in an arc of the meridian and by multiplying the number so found by the length of a pace. The instruments most frequently employed by early astronomers were divided circles and compasses with simple sights, which allowed the line of vision to be directed to the star under observation and its direction as compared with some other line of sight to be measured. Ptolemy's ring or astrolabe, for example, described in the 5th book of his Almagest and used to identify the relative positions of the stars and planets, was composed of 2 concentric vertical circles. The outer circle, about 16 inches in diameter, was fixed and graduated. It supported the interior ring, which was movable, and carried the 2 sights. There was also a geometric square, which was used in a manner analogous to that of a table of logarithms. Various forms of apparatus for the measurement of horizontal and vertical angles were early developed, and as the study of the heavenly bodies developed to a point where it was useful in navigation, the cross staff or back staff was invented, consisting of simple sighting bars with cross pieces suitable for the calculation and measurement of such angles as the heights of the heavenly bodies above the horizon and their distance from one another. Quadrants of one form or another, with a sighting bar and divided circular scale, and astrolabes or celestial circles, also for the direct measurements of angles, were employed. Many of these, by the Middle Ages, were examples of accuracy of division. A quadrant designed by Tycho Brahe (1546 1601), for example, was of 19 feet radius and had its circumference graduated to single minutes. Various forms of armillary spheres were constructed in which the stars were placed in their relative positions on great circles of the celestial sphere. Such devices served for much of the early astronomical work, taking the place of modern star charts. Tycho Brahe, like his predecessors, employed wooden instruments. One of these was a large Ptolemy's ring, surmounted by a post carrying horizontal arms, by which it was turned in bearings like a capstan, so that the ring could be brought into any vertical plane. Tycho Brahe also constructed a mural circle, by means of which vertical angles could be measured. Hence it was by using the naked eye and rudimentary instruments that he accumulated observations of such precision that they served Kepler as the basis of the researches which led to the discovery of the laws of planetary movement. The eye can distinguish an object whose diameter is equal to about 1/3000 of its distance, which corresponds with an angular diameter of about 1 minute of arc. This was the measure of the precision of early observations. Its value may be appreciated by stating that it corresponds with the diameter of a lead pencil seen at a distance of 70 feet. The telescope, by increasing the distance at which objects can be distinguished, therefore has been and is now the chief reliance of the astronomer in determining position. While the naked eye today may be said to have been very largely supplanted by spectroscopic and photographic observation, Yet the telescope has constantly met the demands of astronomers as its power has increased and its scope widened. By chance or otherwise, it was found by a Dutch spectacle maker, Lippershey, about 1608, that two lenses, when placed at some distance apart, would act to magnify distant objects, just as a single lens would enlarge the image of a nearby object. This action of the lens can be explained by considering the effect on a prism of transparent material placed in the path of a beam of light. When a beam of light falls on one of the angular faces of the prism at a direction other than perpendicular to the face, it is forced to change its direction on account of refraction, due to the change in medium. That is, a ray of light passing obliquely through air into a denser medium, such as glass, is bent toward the perpendicular, and in passing out from a denser to a rarer medium, is bent away from the perpendicular. A lens may be considered as a collection of prisms of constantly changing angles, so that the effect would be to bend parallel rays coming from a point at infinite distance in such a way that they would all be brought to a single point known as the focus. Consequently, a telescope may be regarded as a light gatherer. The importance to astronomy of Lippershey's invention can be appreciated from the fact that as soon as Galileo heard of it, he constructed such an instrument which, hardly the size of a small toy spyglass, magnified 3 times, or brought the heavenly bodies 3 times as near. He applied it to celestial observation in 1609. The value of the telescope as an astronomical instrument became apparent immediately. It was from the use of his optic tube, as he called it, that Galileo arrived at the conclusion that Ptolemy was wrong and Copernicus right. How will become apparent from a consideration of the discoveries made by Galileo. He did more than this, however, for by the application of the telescope to the observation of the stars, he became in truth the founder of our modern science of astrophysics. Galileo saw hosts of stars never before revealed to the unaided eye. The 6 stars in the Pleiades now appeared as 36, and various nebulous objects of light, such as the Milky Way, were found to consist of multitudes of fine stars clustered together. But his crowning achievement occurred on January 7, 1610, when in turning his telescope toward Jupiter he discovered 4 satellites of that planet, and determined that their periods of revolution around Jupiter ranged from about 42 hours to 17 days. Here was a miniature system similar to that conceived by Copernicus. Was it any wonder that Galileo abandoned the Ptolemaic teaching? Thus Galileo was able to strike a serious blow at the infallibility of Aristotle and Ptolemy, by whom no mention had been made of the existence of such extra bodies. At this time, however, others besides Galileo were working with the telescope, among them Thomas Harriot (1560 1621) in England, Simon Marius (1570 1624), and Christopher Scheiner (1575 1650) in Germany. Thenceforth observational astronomy with the telescope was anchored on a firm basis. As was quite natural, telescopes eventually formed an important part of the equipment of the observatory of Tycho Brahe and of John Kepler (1571 1630). In one of Kepler's works on optics is contained a suggestion for the use of a convex lens for an eyepiece in the construction of the telescope. Galileo's instrument consisted of a lead tube containing a large double convex lens, which served as an objective, and a small double concave lens at the eye end, in order to give an erect image, an arrangement which finds its counterpart in the modern opera glass. Kepler's suggested improvement provided a more efficient and fairly modern astronomical telescope. The actual construction of an instrument of this type, however, is credited to Scheiner rather than Kepler, who was notably deficient in mechanical skill. After considerable experimenting by various astronomers and instrument makers, it was found that a comparatively small objective with a considerable focal length was more useful and effective. In 1672, Cappani of Bologna constructed an instrument of this kind 136 feet long, while Auzout actually made a telescope 600 feet in length, which, however, failed to work. These, of course, were skeleton structures not mounted in tubes. Perhaps the best of them were those of Huygens (1629 1695), whose skill in grinding lenses stood him in such good stead that he was able to construct a telescope with which he determined the ring of Saturn. Huygens' telescope had considerable focal length. He placed the object glass on a tall vertical pole or staff, so balanced that it could be moved in any direction by means of a cord. The observer on the surface of the Earth was supplied with an eyepiece, which he maintained in a straight line with the star he was observing by means of a cord. All these telescopes were refractors. They were subject to certain inherent defects, chief among which was the difficulty of bringing to a single focus all the rays of different colors. The 17th century philosophers believed it impossible to overcome the unequal refrangibility of the different colored rays of light, which produced chromatic aberration, and resulted in an image indistinct for the blurring of various colors. Accordingly, they gave up the idea of perfecting the refracting telescope, and directed their attention to constructing an instrument on a different principle, using a concave mirror to form the image of the object observed. Mersenne, in 1639, suggested the employment of a spherical mirror, but the idea appears to have been dropped. Quite independently, James Gregory, in 1663, proposed a similar arrangement, using, however, a parabolic in place of a spherical mirror. At that time he could not find a workman able to construct such a mirror. In the Gregorian instruments the parabolic reflector is placed at the lower end of the tube, while on its axis and a short distance beyond its focus is placed a small concave reflector. The light from the distant object falls upon the large mirror, from which it is reflected back to the small one, which throws it back through a hole in the center of the large reflector. It then passes into the eyepiece, which, indeed, in Gregory's time had been much improved by Huygens. Gregory's efforts turned Newton's attention to reflecting telescopes. In 1669 he cast his first disc and began to grind it, but it was not until 1672 that he had real success. Then he made two small instruments, one of which was only about an inch in diameter, with a magnifying power of about 38. The principle of Newton's telescope differed from that of Gregory's in that it had a small plane mirror placed in the cone of light from the reflector at an angle of 45 degrees. Being placed inside the focus, this mirror brought the light cone at right angles to its original direction, thus forming the image outside the tube and obviating the necessity of a hole in the parabolic reflector. About the same time that Newton completed his instrument, the Cassegrain construction was proposed, which was similar in construction to the Gregorian telescope, except for the small mirror. In the Gregorian this mirror was concave. Cassegrain (1672) proposed the use of a concave mirror inside the focus. It brought the light from the object to a focus through a hole in the center of the large parabolic mirror. Owing to the difficulty in obtaining a suitable mirror alloy, little progress was made for some time in constructing reflecting telescopes. In 1718, however, Hadley, the inventor of the sextant, constructed one on the Newtonian principle, 5 feet in length. the instrument magnified over 200 times and revealed as much as the old refracting telescopes. Perfect as this Newtonian telescope seemed to be, the Gregorian type held the field until 1774. End of section 2. Section 3 of The Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Avai in July 2015. The Science History of the Universe, Volume 1, edited by Francis Rolt-Wheeler. Astronomy. Chapter 2. The Evolution of Astronomical Methods of Observation. Part 2. By using a small Gregorian telescope, Herschel had his attention directed to the wonders of astronomy. His income being too limited to purchase an instrument, he set about making one for himself. During his life he is said to have made upward of 400 telescopes, mostly of the Newtonian type. Among his earliest efforts was the construction of a 5-foot reflector, which was a wonderful success. Then came one 7 feet in length. The largest of his instruments was completed under George III in 1789. This telescope surpassed all his previous efforts, for it was actually 40 feet long and had a reflecting mirror 4 feet in diameter. The story of Herschel's work with this great telescope would fill a volume. The largest telescope of the reflecting type was constructed by Lord Rosse, an Irish peer, and used at Parsonstown. It had a mirror of 54 feet focus and a diameter of 6 feet, but it could be used only for observations on or near the meridian. While out of use for many years, it long held the record for size, which, however, is now taken by the 100-inch reflector recently completed for the Mount Wilson Solar Observatory, California. The case of the reflecting telescope, which, as we have seen, had been all but abandoned on account of its chromatic aberration by the 17th century astronomers and physicists, was not as hopeless as they believed. Notwithstanding Newton's dictum that it was useless to try to improve it, owing to the impossibility of producing refraction without dispersion, Euler read a paper before the Berlin Academy in 1746, proving mathematically the possibility of correcting both the spherical and chromatic aberration of an object glass. Upon reading Klingenstierna's paper corroborating Euler's views, John Dolland made a series of most valuable experiments which led him to the solution of the problem of the achromatic object glass, namely, that by properly combining two kinds of glass, flint and crown, he could unite the colored rays fairly well and still have refraction to unite the incident rays to form an image. Dolland's discovery occurred in 1758. His work soon became famous. He was surely master of his subject and had a clear field for many years. Like other opticians, he labored under great difficulties in securing glass suitable for telescopes of any diameter. Fortunately, a genius had taken hold of this problem in the person of Guinon, a Swiss watchmaker, who, after long experimenting, solved the problem of making fine discs of optical glass. He associated himself with the celebrated Fraunhofer in 1805, and they successfully made optical glass discs up to 15 inches aperture. To Fraunhofer are due many of the most important discoveries in the theory of the achromatic objective. With proper optical glass and methods of correction, the refracting telescope soon came into its own. The size of the objectives was increased so that sufficient amounts of light were gathered to form a distinct image. The best makers of Europe gradually developed both lenses and mountings, so that precision of measurement and ease of adjustment were secured. It was in the United States that the best work in this field began to be carried on. The lenses of Alvan Clark gained an international reputation. An objective 30 inches in diameter was made by him for the Russian observatory at Pulkowa, soon after a 26-inch telescope had been completed for the U.S. Naval Observatory in Washington. These were succeeded by the 36-inch instrument of the Lick Observatory and the 40-inch telescope of the Yerkes Observatory, with both of which results in proportion to their increased size have been obtained. The 17th century really marks the beginning of instrumental work and accurate measurements in astronomy. The vernier, which made it possible to subdivide linear and circular scales with accuracy, made its appearance in 1631. In 1640 the optical axis or line of direction of the telescope was practically defined, and the micrometer was invented by William Gascoigne (1612 1644), which was the forerunner of the filar micrometer, so essential to modern astronomy, where an image at the focus of a telescope can be measured. The micrometer is indeed an important adjunct to the telescope, for, unless angular distances can be measured, the mere bringing nearer of the celestial bodies would have but a limited amount of usefulness. In the micrometer of William Gascoigne, 2 pointers carried by a single screw were placed at the focus of a telescope. When these pointers were parallel, they pointed to 0. But by revolving the screw they could be separated, and the number of revolutions or parts of a revolution could be read from a divided head. Consequently, all that it was necessary to know was the distance between 2 successive threads of the screw, in order to obtain an exact value for any distance which the pointers might separate. Now, if it were desirable to determine the angular distance between 2 stars, each pointer was set on a star, and the distance between them was thus gradually measured, so that by simple mathematics the corresponding angular distance could be computed. Micrometers soon became an important part of exact observation with a telescope. Auzout and Picard made subsequent improvements, so that finally a micrometer resulted in which a spider filament was placed on a frame moved by a screw with graduated head, thus enabling increased precision of observation to be obtained. This is the fundamental device now used with various improvements and refinements. Römer, who was the first to determine the velocity of light, improved the micrometer in 1672 by adding springs to take up the lost motion. He also constructed the first meridian telescope in 1689. By the middle of the 17th century the use of telescopic sights for determining the position of the stars had become established. The precision of the observations of that epoch may be estimated at 10 seconds of arc, which corresponds to the diameter of a lead pencil seen at a distance of about 550 feet. Methods and instruments continued to improve. The observations of Lalande attained a limit of precision of 1 second of arc, corresponding to a pencil at 5,500 feet. At the beginning of the 19th century great improvements were made. In 1875 the limit of precision had been reduced to 1/2 a second, which removes the lead pencil to 11,000 feet, or more than 2 miles. For minute measurements one of the most useful devices has been the heliometer or divided object glass micrometer, the first really available type of which was constructed by Fraunhofer for the observatory at Königsberg. In this instrument an object glass or lens is used, which is divided along its diameter. The 2 parts of the glass are mounted so that they can be moved laterally with respect to each other. Consequently each half supplies a distinct image of the same object, but separated by a strictly measurable amount. Thus, if a double star is under examination, the 2 half lenses into which the object glass is divided can be moved until the upper star in one image is brought into coincidence with the other star in the lower image, so that the distance apart becomes known by the amount of motion employed. By using screws with heads of considerable size to move the halves of the object glass, the heliometer can be read to the 1,000th part of a revolution, and in the case of the Königsberg instrument such a division, equivalent to 1/20th of a second of arc, could be measured with accuracy. This new instrument, which was not mounted until 1829, 3 years after the death of Fraunhofer, was at once employed by Bessel to solve the problem of star distances. His measurement of the parallax of the star known as 61 Cygni, corresponding with a distance about 600 times that of the Earth from the Sun, not only was considered ascertained beyond question, but is spoken of by Miss Clerke as memorable as the first published instance of the fathom line so industriously thrown into celestial space, having really and indubitably touched bottom. In 1874 the heliometer was applied to the observation of the transit of Venus, and again in 1877, when Mars came into opposition with the Sun, Sir David Gill, using the heliometer, made a valuable determination of the solar parallax, obtaining a value of 8.78 seconds, corresponding with a distance of 93,080,000 miles. By this time the heliometer had become an accepted method for improving astronomers' knowledge of the Sun's distance. A number of heliometers were employed in cooperation at different points of the Earth's surface, the work of Professor Elkins at Yale in connection with Sir David Gill at the Cape of Good Hope Observatory being especially notable. Another modern development of telescopic astronomy has been the direct measurement of the magnitude and brightness of a star, thus superseding to a great degree the judgment of the eye upon which the older astronomers had depended from the days of Hipparchus. The photometers, light measurers, used with telescope for this purpose consist either of those designed to cut down the amount of light furnished by a measurable amount and thus cause the star to disappear, or those in which conditions are so arranged that the light of the star appears just equal to some standard light. Under the first head is the so-called cat's eye, in which a wedge of dark neutral tinted glass is placed close to the eye, either at the eyeball of the eyepiece or at the principal focus, where the micrometer wires are usually placed. As the wedge is introduced until the star just disappears, the graduation is read, which graduation can be reduced to a scale of magnitudes. In the other class of photometers the light of the star is compared with an arbitrary artificial star formed by light from an oil lamp shining through a small aperture. To Huygens is due the application in 1655 of the pendulum to the practical measurement of time, thus giving us a clock so regulated that it was possible to make accurate time observation. The invention of the pendulum clock, patented in 1657, therefore marks a distinct epoch in astronomy. The most usual and most useful form of mounting for a telescope is the equatorial, the principal axis of which is inclined at an angle equal to the latitude of the observatory, and is directed toward the North Pole in the northern hemisphere and toward the South Pole in the southern hemisphere. The axis of the instrument is thus parallel to the Earth's axis of rotation, and is therefore called the polar axis. It carries a graduated circle which is parallel to the celestial equator, known as the hour circle, from which circle may be read the hour angle of the body upon which the telescope happens to be pointed. The polar axis also carries the bearings of the declination axis, which is perpendicular to the polar axis and carries the telescope itself and the declination circle. When the equatorial telescope is directed toward a star or a planet, it is necessary only to use clockwork machinery to cause the polar axis of the instrument to turn with a uniform motion in order to follow any star or planet which otherwise would soon be carried out of the field of view by the rotation of the Earth. The equatorial also enables the observer to look at once to a particular part of the heavens where a given body is expected to be at a given time. The mounting for a modern equatorial telescope requires large and heavy moving parts. Where a solar or stellar image is desired, it does not seem desirable to employ such a heavy mechanism. To Léon Foucault, about 1868, the idea occurred to construct a fixed telescope with a mirror, moving with 1/2 the angular velocity of the sun, deflecting a beam in a fixed direction. Such an instrument was constructed and was employed with good results, although its operation was marred by imperfections in its driving mechanism. However, the device did not attract much attention until plans were made in the eclipse expedition of 1890 for extensive photographs of the phenomenon. It was proposed to use the instrument in connection with a second mirror to produce an image which would not move. This device, now called a ccelostat, was found admirable for eclipse photography. Experiments were made at the Yerkes Observatory to construct such an instrument for solar work. The work was subsequently transferred to the Carnegie Institution Observatory on Mount Wilson. An extension of the same principle may be found in the tower telescope of that institution, where a ccelostat is mounted on the top of a skeleton tower, and a beam of light is reflected to a laboratory beneath. Today the most modern and efficient reflecting telescope of large size is the 100-inch instrument designed for the same observatory by Professor G. W. Ritchie. At the present time both refracting and reflecting telescopes are in use and have been brought to a great degree of perfection. Just which is the better it would be hard to say. The old speculum metal reflector has been almost discarded, and glass, coated with silver, has been substituted. The glass is much superior to the metal, as it can be figured more accurately, and if tarnished the silver can be removed without changing the figure of the mirror. Again, much study has been given in France to a form of telescope known as the equatorial coudé, in which the optical axis of the telescope is parallel to the axis of the Earth, and the light of the star is reflected into it by two mirrors. Such an instrument, constructed for the Paris Observatory, has been very convenient for the astronomer, who can sit in his chair and observe the stars as easily as he can use his microscope. But the loss of light and definition by the double reflection, as well as the deflection of the mirrors and the varying temperatures to which the different parts of the instrument are subjected, render this construction far from perfect. End of section 3. Section 4 of The Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Abai in July 2015. The Science History of the Universe, Volume 1, edited by Francis Rolt-Wheeler. Astronomy. Chapter 3. The Evolution of Astronomical Instruments and Methods. The Rise of Astrophysics. The Spectroscope and its Modifications. To gain a knowledge of the composition and nature of the celestial bodies is the fundamental problem of astronomy. Unable to bring a celestial body or a specimen from it, except in the rare case of a meteorite, to the chemical laboratory for study, the astronomer is dependent entirely on a study of the energy that it emits in the form of light and heat rays. Strange as it may seem, these rays furnish as true a record of their birth and life history as if a sample from the distant star had been tested in the assay furnace or with the reagents of the chemist. The simple instrument called a spectroscope gives an accurate and permanent record which affords complete data for the studies of the astronomer. White light is composed of various forms of vibration, which, taken by themselves, will supply light of various colors from red to violet. It was found by Sir Isaac Newton, in passing a beam of white light through a prism, that not all of the rays are bent equally toward and away from the perpendicular, but that the amount of bending depended upon their color, or, as it is now termed, their wave-length and position in the solar spectrum. Thus, when he permitted a beam of white light, emerging from a hole in a shutter, to fall upon a prism in a dark room, he found that there was produced after its emergence a brightly colored band, with the red at one end, where the waves were refracted the least, and shading through yellow and green to violet, where the waves were bent or refracted most. Consequently, if there were a source of light capable of furnishing one color, and that only, it would be obvious, wherever that color appears in the bright band produced by the prism, that it radiated from a particular source. Before 1753, a young Scotchman, Thomas Melville, noticed that when various compounds of sodium were introduced into an alcohol flame and viewed through a prism, there appeared a particular shade of yellow light, which was always bent or refracted to a fixed and definite degree. Others repeated these experiments, and finally Fraunhofer (1787 1826), a great optician of Munich, rediscovered this deep yellow ray and found its place in the spectrum. The same phenomenon was noticed by many other experimenters. Indeed, the omnipresence of the yellow light was often an embarrassment in spectral research. That this yellow line was due to sodium was pointed out by William Swan. Finally, it was noted that the distribution of sodium was so general and the prism test of its presence so delicate that its absolute exclusion was well nigh impossible. Before Fraunhofer's experiments, the round hole in the shutter of Newton had been supplanted by a slit or crevice about 1/20th of an inch wide, and the spectral band thus formed from sunlight was not only continuous, but free from overlapping images, so that the colors were shown in their purity, crossed by 7 dark lines. In the course of his experiments, Fraunhofer not only used the slit, but added to it the telescope of the modern spectroscope. He was surprised to find not merely 7, but thousands of dark transverse lines, many of which he mapped, counted, and designated by the letters of the alphabet. Not only did he examine sunlight in this way, but also the light of the moon and planets, and found that stellar spectra too were crossed by the same dark lines. In the case of certain stars there were even dark bands. He found that one, or rather a pair of solar lines which he had marked in his map with the letter D, coincided exactly with the yellow beam which accompanied incandescent sodium vapor. The coincidence was noted by Fraunhofer, but the explanation came in 1859 from the distinguished German physicist Professor Gustav Robert Kirchhoff (1824 1887). He it was who sent a beam of bright sunshine through sodium vapor and discovered that the D line of Fraunhofer, instead of being effaced by the flame, was strengthened. The same held true with iron. The inference was of course drawn that sodium and iron were constituents of the glowing atmosphere of the Sun, and that light of the particular wavelength in passing through such an atmosphere was absorbed. This particle has been formulated by Miss Clerke as follows: Substances of every kind are opaque to the precise rays which they emit at the same temperature; that is to say, they stop the kinds of light or heat which they are then actually in a condition to radiate. But it does not follow that cool bodies absorb the rays which they would give out if sufficiently heated. Hydrogen at ordinary temperature, for instance, is almost perfectly transparent, but if raised to the glowing point, as by the passage of electricity, it then becomes capable of arresting, and at the same time of displaying in its own spectra, light of 4 distinct colors. In these few words we have the essence of spectroscopic chemistry and astrophysics. Materials of the Earth, when heated to incandescence, give a bright line spectrum characteristic of the individual element, but the same materials in the Sun show a spectrum marked by dark lines. While spectrum analysis was applied to chemistry and terrestrial materials by Bunsen, Kirchhoff worked industriously and made a map of the solar spectrum some 8 feet in length, in which the various lines of the elementary bodies were represented. The spectroscope, as constructed by Kirchhoff, consisted of a slit placed at the principal focus of the convex lens to make the rays parallel for their passage through the prism. In order to secure greater dispersion, several prisms were added and the emerging beam was passed through the telescope to form an image of the spectrum. The new instrument at once presented an enormous number of lines for study, not only of the Sun, but of various other celestial bodies. It was soon applied to the observing end of an astronomical telescope, so that the celestial image was formed directly at the slit of the spectroscope. By increasing the number of prisms, the dispersion of the spectroscope can be increased, and a longer spectral band produced, in which otherwise closely adjacent lines are increasingly separated. But in passing through a number of prisms there is considerable loss of light by reflection and absorption, so that a limit is soon set to the number of prisms employed. Another form of spectroscope, which makes use of a grating or a number of fine lines ruled very closely together on a transparent or a reflecting surface, has been found to possess greater dissolving power without any accompanying loss of light. In fact, the resolving power of a perfect grating depends simply upon the total number of lines it contains, so that the light efficiency per unit area may be as great for a large grating as for a small one. The principle of the grating depends upon the interference of the various minute light waves caused by a series of lines, amounting to from 10 to 20,000 to the inch, ruled on a transparent or a reflecting surface. The mathematical discussion of the formation of a spectra by the interference of the light waves in passing through or being reflected from such a grating can hardly find a place here. The result, however, is essentially the same as in the case of a prism. As soon as the dispersion of light was obtained by this means, it was found that it could be studied quantitatively, and that the grating could be used for astronomical measurements with as great facility as the prism spectroscope. Lewis M. Rutherford of New York was able to make excellent gratings about 1864, but it remained for Professor Henry A. Rowland (1848 1901) at the Johns Hopkins University to construct a dividing engine with a screw, practically free from error, which would move a small plate of polished speculum metal by regular intervals of 1/15,000th of an inch under a diamond point which traced sharp and regular lines. This machine not only was remarkably sensitive in its action, but automatically compensated for any minute irregularities in the screw. It was made to work at a constant temperature. It automatically proceeded with its ruling night and day until a grating of the desired length was completed. Professor Rowland for the first time ruled gratings on concave surfaces, and used them in place of the prism of the ordinary spectroscope. The spectra obtained with these diffraction gratings, in conjunction with special lenses, were many feet in length, and could be photographed in sections on photographic plates, each of about 20 inches in length. The grating spectroscope has been modified by Professor A. A. Michelson of the University of Chicago, who has devised a new form of grating in which a series of glass plates precisely equal in thickness are placed one on another like a flight of steps. A parallel beam of light, when transmitted through them, is resolved into spectra of a very high order, exceeding even those of Rowland's largest gratings, so that compound lines in the spectrum can be studied with facility. The application of the spectroscope has made of astronomy an experimental science, with methods and instruments for research and future progress fully as promising as may be found in any of the physical or natural sciences. The spectroscope has not only amplified astronomy, but it has developed the new science of astrophysics, in which astronomy is combined with physics. New methods and instruments for research already have brought to light striking discoveries which have compelled the modification of older astronomical and cosmical theories. In connection with the spectroscope, it is possible to measure the temperature of the radiations sent out from the Sun and the stars with a high degree of accuracy by means of the bolometer, a sensitive thermometer invented by Professor S. P. Langley. It consists of two very fine threads of platinum wire about 1/2500th of an inch in thickness, mounted side by side within a constant temperature chamber. On one of these wires the radiation is permitted to fall, while the other is carefully shielded. Any change in the temperature of the wire on which the light or heat waves fall produces a difference in its electrical resistance that can be measured with a high degree of precision, so that a difference of less than 1/1,000,000th of a degree in the temperature can be clearly indicated. The spectrum formed by the spectroscope is caused to move slowly across the exposed platinum wire of the bolometer, and a galvanometer in the circuit reflects from its mirror a spot of light upon a photographic plate, so that the deflections of the magnetic needle are photographed and registered, thus indicating the intensity and energy at the different parts of the spectrum. This instrument was first used by Langley to determine the amount of heat received from the Sun on the top of Mount Whitney in 1881, and since that time it has been employed by him and his successors at the Astrophysical Laboratory at Washington and also at Mount Wilson. The problem that the bolometer seems capable of solving is to determine the atmospheric absorption of light and heat in the passage of the Sun's rays to the Earth. It has also been used to measure the heat spectrum of the Moon and some of the brighter stars, in the case of the former showing that the Moon is very cold, as there is a considerable quantity of heat radiated having a wavelength greater than that of the heat radiated from a block of ice. After the fundamental work of Kirchhoff in identifying the spectral lines of the Sun and the stars with various terrestrial materials, it was but natural that the composition of stars as shown in their spectra should be thoroughly attacked by astronomers. Among the first of these was Sir William Huggins, who devoted the greater part of a useful scientific life to research of the heavenly bodies, especially as revealed by the spectroscope. In 1862 Huggins, Secchi and Lewis M. Rutherford began their researches in stellar spectra that enabled them to classify and compare the spectral bands furnished by the different stars. It was the spectroscope in the hands of Sir William Huggins that made possible the solution of the riddle of the nebulae, the nature of which for long years had been a vital point of discussion among astronomers. On August 29, 1864, directing his spectroscope to the planetary nebulae in Draco, Huggins saw, instead of the bright band he anticipated, a single line which subsequently was resolved into 3 lines. Thus he proved that the nebula was not an aggregation of stars or incandescent solid materials, which would have afforded a continuous spectrum crossed by dark bands and a luminous gas. The effect of the spectroscope on astronomical research is thus summarized by Professor Hale. In astronomy, the introduction of physical methods has revolutionized the observatory, transforming it from a simple observing station into a laboratory. The interest of the students of astrophysics is no longer confined simply to celestial phenomena. For astrophysics has become, in its modern aspect, almost an experimental science, in which some of the fundamental problems of physics and chemistry may find their solution. The stars may be regarded as enormous crucibles, in some of which terrestrial elements are subjected to temperatures and pressures far transcending those obtainable by artificial means. In the Sun, which appears to us not merely as a point of light like the stars, but as a vast globe whose every detail can be studied in its relationship to the general problem of the solar constitution, the immense scale of the phenomena always open to observation, the rapidity of the changes, and the enormous masses of material involved provide the means for researches which could never be undertaken in terrestrial laboratories. Hence it is that astrophysics may equally well be regarded as a branch of physics or as a branch of astronomy. The great advantage of the spectroscope over the eye or the direct image from the photographic plate is its ability to analyze the action of light. While the intensity of light suffers in its journey through space, yet the nature or character of the light undergoes practically no change, so that the light from a distant star, separated from the Earth by an interval that seems to us almost infinite, can be received in our spectroscope and be resolved into a spectral band with difficulty but slightly greater than that which would be found in the employment of a luminous source of light at the opposite end of the laboratory table. The spectroscope, therefore, can be used in astronomy to determine the composition of a distant body according to the principle of spectrum analysis. But this is not all. It also enables the determination whether the light from a luminous body in the heavens is approaching or receding, and whether the light emitted from such a body is the same today as it was yesterday or half a century ago, and whether it comes from one or more bodies which the eye and perhaps the telescope cannot separate, but which are distinctly separate. Hence the astronomer is only too glad to remove the eyepiece from his telescope and put in its place some spectroscopic device which will analyze the light into separate colors and give him much valuable information as to the constitution and motions of even the most distant star. The value of the spectroscope is greatly increased by the application of photography. The general nature of a spectroscopic investigation can best be described by abstracting from Professor Hale its description of solar spectrum analysis. Sunlight must be reflected from a mirror to a heliostat, driven by clockwork to maintain the beam in a fixed direction, to the slit. Between the slit and the heliostat a lens is introduced, for the purpose of forming an image of the sun upon the slit. When the illumination is secured in this way, the whole grating is filled with light from the diverging rays. The grating then produces an image of the solar spectrum upon the photographic plate, where it may be recorded by giving a suitable exposure. To facilitate an accurate comparison, the solar spectrum is photographed side by side on the same plate with the spectrum of the substance whose presence in the sun is to be determined. In order to accomplish this, one half of the slit is covered, and the sunlight is admitted through the other half. Thus the solar spectrum is photographed on one side of the plate. After this exposure is completed, the sunlight is shut off, and the screen in front of the slit moved so as to cover the half previously open and to uncover the other half. The image of the sun on the slit of the spectroscope is then replaced by an image of an electric arc light burning between two poles of iron. The spectrum of the iron vapor is thus produced on the plate, and a strip of this spectrum is photographed beside the strip of solar spectrum. The bright lights of iron are represented in the solar spectrum by corresponding dark lines which accurately image them in position. In Rowland's work on the solar spectra, thousands of lines were found to correspond with the iron lines given by the electric arc. The same process can be employed to determine the presence of other substances in the sun. In the case of metals, the electric discharge may be caused to pass between two metallic rods, or fragments of the metal may be placed in a hole drilled in one of the carbons of an ordinary electric arc lamp. In the latter case the spectrum of carbon, and also of impurities which the carbon poles always contain, will appear on the plate with the spectrum of the metal in question. But these extra lines may always be identified and usually give no trouble. The identification of the solar lines, however, is not always so simple as in the case of iron. Many substances are doubtfully represented in the Sun by only a small number of lines, and it is sometimes very difficult to decide whether a few apparent coincidences are sufficient to warrant one in drawing definite conclusions. The matter is usually determined by ascertaining whether certain well-known groups of lines, which for various reasons are considered to be especially characteristic of an element, are actually represented. If these groups are absent, an apparent coincidence with certain less characteristic lines belonging to the same element should be regarded with suspicion. In the case of gases the comparison is effected by the aid of vacuum tubes, in which the gas, usually at low pressure, is illuminated by an electric discharge. Thus the lines given by a hydrogen tube in the laboratory have been shown to coincide in position with lines ascribed to hydrogen in the Sun. After many years of study of the solar spectrum by these methods, Rowland reached the conclusion that the chemical composition of the Sun closely resembles that of the Earth. Certain elements, such as gold and radium, iodine, sulfur and phosphorus, chlorine and nitrogen, have not been detected in the Sun. But this does not prove that they are certainly absent, as their level in the solar atmosphere, or in the low degree of their absorptive effects, might prevent them from being represented. On the other hand, various substances not yet found on the Earth are shown by many unidentified lines of the solar spectrum to be present in the Sun. Some, if not all of these, will probably be discovered by chemists, just as helium was found by Ramsay in clevite. Rowland remarked that if the Earth were heated to a sufficiently high temperature, it would give a spectrum closely resembling that of the Sun. End of section 4.
Section 5 of The Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Marianne Spiegel. The Science History of the Universe, Volume 1, edited by Francis Rolt-Wheeler. Astronomy. Chapter 4. The Evolution of Astronomical Instruments and Methods. Celestial Photography. After the spectroscope, photography has been the most useful tool of the astronomer, and to its aid must be credited some of the most important work of the latter half of the 19th century. For the development of celestial photography as outlined in the present chapter, an interesting paper by Professor E. Barnard supplies in large part the material. According to Professor Barnard, the application of photography to astronomy may be said to date from the very first announcement of Daguerre's wonderful discovery of the production of a permanent image by the effect of light upon silver salts. The celebrated French astronomer, Arago, quickly foresaw its great possibilities, especially in the faithful delineation of the surface features of the Sun and the Moon, for these two objects at least were bright enough to register themselves with the sluggish materials then in use. It was of course obvious to astronomers and physicists that the formation of an image on a sensitized plate was in no way different from that produced at its focus by the telescope lens, and that the image of a celestial body would be produced as well as any other. It was from America that the first practical work came, and within less than 1 year from the announcement of Daguerre's discovery, in March, 1840, Dr. John W. Draper of New York City succeeded in getting pictures of the Moon which, though not very good, foreshadowed the possibilities of lunar photography. 5 years later, at the Harvard College Observatory, Bond, with the aid of Messrs. Whipple and Black of Boston, succeeded in obtaining still better pictures of the Moon with the 15-inch refractor. These pictures on daguerreotype plates aroused great interest, especially in England. However, the difficulties encountered led to failures generally, except in the case of De la Rue, Dancer, and one or two others. In 1858 De la Rue, using a 13-inch metal speculum reflecting telescope, without clockwork, and guiding it by following a lunar crater seen through a plate, made the most important of the early efforts at lunar photography. His photographs were the best until those made in America in 1860 by Dr. Henry Draper, son of the illustrious John W. Draper. He secured excellent photographs of the Moon, superior to any previously made, and capable of considerable enlargement. These pictures were the best taken until Lewis M. Rutherford began his remarkable work about 1865. His admirable photographs of the Moon were made with a refractor of 11-inch aperture, which, constructed under his immediate supervision, was the first telescope corrected especially for the photographic rays. The completion of the Lick Observatory in 1888 marked another decided advance in astronomical photography, especially of the Moon. The great focal length of this magnificent instrument gave an unenlarged image of the Moon about 6 inches in diameter, which in itself was a great advantage. Good results were also secured with the Yerkes refractor. Admirable lunar photographs have been made by Messrs. Loewy and Puiseux with the equatorial coude at Paris, and have shown the usefulness of this singular instrument for such work. The first picture of the Sun seems to have been made on a daguerreotype plate by Fizeau and Foucault in 1845, says Professor Barnard. During the total eclipse of the Sun on July 28, 1851, a daguerreotype was secured with the Königsberg heliometer, 2.4 inches in diameter and 2 feet focus, by Dr. Buch, which appears to have been the first photographic representation of the corona. It showed considerable detail quite close to the Moon. But in the early eclipses photographic work seems to have been devoted mainly to representations of the solar prominences, which at that time were as rarely seen as the corona itself. During the eclipse of 1869, however, Professor Hymes secured a photograph which showed the brighter structure of the corona. Similar pictures were also obtained during the same eclipse by Mr. Whipple, of Boston. The corona was also slightly shown on pictures made as early as 1860 by M. Sarratt. None of them, however, showed more than slight traces of the corona, extending only for a few minutes of arc from the Moon's limb. Nearly all the pictures seem to have been taken with an enlarging lens, which was doubtless used to get the prominences on a larger scale. The first really successful photographs of the corona were obtained at the eclipse of December 22, 1870, when it was shown on the plate to a distance of about half a degree from the Moon's limb. This picture, made by Mr. Brothers at Syracuse, Sicily, showed a considerable amount of rich detail in the coronal structure. The same can also be said of the photographs of this eclipse taken by Colonel Tennant and Lord Lindsay's party. These seem to have been the first pictures that really showed the great value of photography for coronal delineation. The eclipse of 1871 was still more successfully photographed, and an excellent representation of the corona, full of beautiful detail, was secured. In 1878 extensive preparations were made to observe the eclipse of July 29 of that year. Photography was to play an important part, though astronomers did not rely very strongly upon it, for it appears that all were prepared to make the customary drawings of the corona. Unfortunately, each person faithfully carried out that purpose. A most suggestive illustration of the uncertainty of such work is found in the large collection of drawings published in a volume issued by the United States Government relating to the eclipse of 1878. An examination of these 40 or 50 pictures shows that scarcely any of them would be supposed to represent the same object, and none of them at all closely resembled the photographs. The method of freehand drawing of the corona, made under the attending conditions of a total eclipse, received its death blow at that time, for it showed the utter inability of the average astronomer to sketch or draw what he really saw under such circumstances. In the eclipses of 1882, 1886 and 1889, photography played a part of increasing importance in the observations. In the latter year there were a large number of amateur photographers who took advantage of the eclipse to make many photographs, which, in a number of cases, were taken in a systematic and scientific manner. At the Lick Observatory a beginning was made in eclipse photography, with an extemporized apparatus, and successful exposures were made. During the eclipse of 1896 important work was done in photographing the flash spectrum, or the momentary reversal of the Fraunhofer lines, which occurs when the edge of the Sun disappears behind the Moon or reappears from it and for an instant exposes the reversing layer, which was first seen by Professor Young at the eclipse of 1870. This photograph was made by a young Englishman, William Shackleton, who, on exposing a plate at the critical instant of the reversal of the lines, caught for the first time the fugitive bright lines, which are visible for only about a minute. This gave a permanent visible record of the phenomenon, which removes it from the class of hasty visual observations whose results depend upon the memory of the observer. The photographing of such a minute point of light as a star is quite different from that of a luminous or brilliant body like the Sun or Moon. Yet it was early essayed, and from the first photograph of a star by Bond in 1850 to the present time, stellar photography has gradually risen to a prominence as remarkable as it is important. Indeed, it is now quite indispensable. The principal reason for the real increase of importance in this work, however, was the successful introduction of the very rapid dry plate. The wet or collodion process, which astronomers soon pushed to its limits, was poorly adapted to the photography of the stars, and of no use whatever for comets and nebulae. Notwithstanding the inherent difficulties of the wet plate, the photographs of the star clusters, etc., of the southern skies, obtained under the direction of Gould, with an 11-inch photographic reflector by the wet process, were of the highest value and showed upon measurement a striking agreement in accuracy with visual work. The same can be said of Rutherford's photographs of the Pleiades, Praesepe, etc., which were made prior to Dr. Gould's, and which were the first photographs of this kind. As early as 1857 Bond had shown, by measurement of a series of photographs of the double star Mizar, that the highest confidence could be placed in measures of star plates. This was subsequently fully verified by Gill, Elkin, and others. As regards absolute accuracy, Dr. Elkin showed in 1889 that measures of a photograph of the Pleiades taken by Mr. Burnham with the great telescope at Mount Hamilton had equal value with the heliometer measures of the same stars. By 1881 or 1882, however, dry or gelatin emulsion plates were beginning to be used with every promise of their ultimate value, as was shown by the photographs of the comet of 1881, which were made by Draper and Janssen. These were the first photographs ever made of a comet. Efforts had been made to secure pictures of Donati's comet in 1858, but without success. It was quite obvious that as soon as satisfactory photographs of stars were secured, some earnest effort would be made to make use of them in a quantitative and systematic way. Previously, for the production of star maps and catalogues, elaborate series of observations were made at the various observatories, and the positions of the stars computed and incorporated in large volumes. At the Royal Observatory at the Cape of Good Hope, Sir David Gill, in 1882, after making some pictures with a large camera of the comet of that year, found that not only did the plates show the stars visible to the naked eye, but a number as small as the 9th or 10th magnitude. Accordingly, it occurred to him that such photographs furnished a novel and excellent method of cataloguing the stars and mapping the heavens, as it was necessary only to measure on the glass negatives the position of the various stars and refer them to certain well-known points of reference. From 1887 to 1891 the entire southern heavens from 18° south declination to the celestial pole were duly photographed. The 500,000 stars found on the negatives were then measured and the magnitude of each determined by Professor J. C. Kapteyn at the University of Groningen, Holland. Thus in 1899 was finished the Cape photographic Durchmusterung, which is published in 3 quarto volumes and contains the magnitude and approximate position of every star photographed, the magnitude of the stars on each plate being reduced to a visual scale. At the time when Sir David Gill began his photographic work, Dr. Barnard states, "The Henry brothers of Paris were making a chart of the stars along the ecliptic in their search for planetoids. They had at this time reached the region of the Milky Way, and the marvelous wealth of stars they encountered on entering the boundaries of that vast zone completely discouraged them from carrying their charts through the rich region traversed by the ecliptic. While hesitating as to the advisability of continuing their work, the photographs of the great comet came to their notice. They were struck with the great number of stars shown on these pictures together with the image of the comet. The idea at once occurred to them that they could use this wonderful process to make their charts. They began at once the construction, with their own hands, of a suitable photographic telescope of 13½ inches diameter for the photography of the stars. This instrument produced exquisite star pictures, which were marvels of definition, as well as photographs of the nebulae, of Saturn and Jupiter, the Moon, etc. It was the success of the Henry brothers' work that led to the International Astrophotographic Congress, which met at Paris in 1886. This congress undertook the organization of an international commission engaged in the preparation of a photographic chart and catalogue of the heavens, and the work since that time has been actively in progress. Uniform instruments of the same aperture and focal length are used at the 18 observatories participating in this work, and 2 sets of plates are being made, one to include all the stars that are capable of being photographed, and the other one those of the 11th magnitude. With this photographic map astronomers anywhere can compile their own catalogues, and portions of such catalogues by various national observatories have already been issued. The method of preparing the chart consists in photographing the whole sky upon glass plates about 8 inches square. Each observatory has had assigned to it definitely its part of the sky, and about 11,000 plates of the size specified will be required to complete the task. Each plate of course carries one or more well determined catalogue stars, whose position is known with accuracy, so that from such points of reference it is possible to determine exactly the position of any other star on the plate. The photographic plate not only did away with the necessity of making the star charts by eye and hand, so essential to facilitate the discovery of planetoids, but it also did away with the necessity of the charts themselves for that purpose. The little planet, which is moving among the stars, now registers its own discovery by leaving a short trail, its path during the exposure, on the photographic plate. The first of these photographic discoveries of planetoids was made by Dr. Max Wolf in 1892, and his observatory at Heidelberg subsequently became a headquarters for discoveries of this kind. Planetoids are now found wholesale in this manner by photography. In the early days of photography nebulae were considered the most unpromising subject for the photographic plate to deal with. Most of these objects appeared so faint that but little encouragement in the direction was offered the celestial photographer. One of the brightest and most promising of the nebulae is that in the Sword of Orion, and this was naturally one of the first of these objects to receive photographic attention. In September 1880 Dr. Henry Draper began photographing nebulae with this object, and succeeded, with 51 minutes exposure, in getting a good picture of the brighter portions on dry plates. This was the first nebulae photograph. It was followed by other photographs, one of which showed stars down to the 14.7 magnitude, which were visually beyond the reach of the same telescope. These pictures marked a new era in the study of nebulae. When the results were communicated to the French Academy by Dr. Draper, Janssen took up the work with a reflecting telescope having a silver on glass mirror of very short focus, constructed in 1870 for the total solar eclipse of 1871. With this Janssen found it easy to photograph the brightest parts of a nebula with comparatively short exposures. Unfortunately for science, the death of Dr. Draper in 1882 put a stop, in America, to the work he had inaugurated, but it was at once taken up in England by Common, who, with the 3-foot reflector, attained rapid and immediate success. His photographs of the great nebula of Orion are still classic. They were a great advance over the work of Draper, for the reflector was not only a larger telescope, but was also better adapted for photographic purposes, and especially for photographing nebulae. In fact, as we shall see in a later chapter on nebulae, much of the progress in their study has been due to photography. The photography of nebulae was carried on with remarkable success at Lick Observatory during the incumbency of Professor James E. Keeler as director. Using the Crossley reflecting telescope, presented to the observatory by Dr. Common, he made a photographic study of nebulae, and reached the conclusion that there are at least 120,000 of the spiral type within the range of this instrument. Professor Perrine, who succeeded to this work on the death of Professor Keeler, believes that 500,000 is nearer the figure, and that with more sensitive photographic plates and longer exposures the number of spirals would exceed 1,000,000. Not only stellar motion but stellar distances can be measured by photography. Professor Pritchard, at Oxford, has used the sensitive plate to sound the celestial depths. His first experiments were undertaken with the star 61 Cygni, and by measuring 200 negatives which had been made in 1886, he derived for that star a parallax of 0.438 seconds, which was in satisfactory agreement with Ball's value of 0.468 seconds. This work was subjected to detailed scrutiny, and the Astronomer Royal was convinced that it was more accurate than that of Bessel's results obtained with a heliometer. This was the beginning of the method of measuring a parallax from photographic plates. Professor Kapteyn showed in 1889 that from such plates, exposed at desired intervals, parallaxes could be derived wholesale. He applied his system in 1900 to a group of 248 stars with encouraging success. In fact, it was suggested that a photographic parallax Durchmusterung should be undertaken after the completion of the astrographical chart of the heavens. When used in connection with the spectroscope, the photographic plate has a field singularly suited to display its possibilities. Here it deals not alone with what can be seen, but it enters into regions where the eye takes no cognizance of things. For though it is partly blind to the light which affects the eye, it can readily penetrate the regions where man, in turn, is blind. By special treatment of the plate, photography registers those rays invisible to the eye and permits their accurate measurement. The spectrograph, or combination of photographic apparatus with spectroscope, must be so arranged as to show with distinctness the greatest number of lines, the individual lines being separated. Consequently, there are various types of spectrograph, depending upon the purpose for which they are to be employed. One of the combinations of the spectroscope with the photographic apparatus is found in Professor Hale's spectroheliograph, which consists of a spectroscope across whose slit the solar image moves at a uniform speed. Instead of the eyepiece there is a second slit which permits light from only a single line to pass and fall upon the moving photographic plate, so that an image of the sun or a sunspot in light of a single wave length can be made to fall upon the plate and thus be recorded. The general effect of photography in astronomy may be summarized in the brief statement that it has removed the astronomer from the eyepiece of the telescope and has substituted the more sensitive photographic plate with its permanent record. Hence it is that the present-day student of astrophysics does not correspond with the traditional idea of the astronomer, says Professor Hale. His work at the telescope is largely confined to such tasks as keeping a star at the precise intersection of two crosshairs, or in the narrow slit of a spectrograph, in order that stars and nebulae, or their spectra, may be sharply recorded upon the photographic plate. His most interesting work is done, and most of his discoveries are made, when the plates have been developed and are subjected to long study under the microscope. End of Section 5. Section 6 of The Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Marianne. The Science History of the Universe, Volume 1, edited by Francis Rolt-Wheeler. Astronomy. Chapter 5. The Law of Gravitation. When the astronomers of old tried to account for the apparent motions of the heavenly bodies by complete systems of epicycles, they must surely have asked themselves, why do the planets move so regularly? What makes them move thus? If they did, they troubled themselves but little to answer the inquiries in anything but a perfunctory way. For the most part they were content to regard the stars as the playthings of divinity, and the cause of their motions, therefore, as a mystery forever veiled to human eyes. Still one astronomer, Anaxagoras, did have some idea of a force which holds the planets in their orbits, and which might be the same as that which operates upon substances at the surface of the earth. After his day, possibly 499 to 427 B.C., The idea seems not to have been expressed by anyone until the awakening of science in the 17th century. Then Kepler darkly hinted at some attractive force, because his discovery of the mathematical curve described by the planets seemed to demand the existence of some constantly exerted controlling force, and also because he had read Gilbert's De Magnete, in which he was made acquainted with the phenomena of electrical attraction. Such a force as he had in mind would act to maintain the motion of the planets and to drive them along in their orbits. But this was hardly the solution of the problem, since, as Galileo found, the motion of a body itself must continue indefinitely unless there is some cause at work to alter or stop it. This formed the first and most important of the laws of motion which, if not independently discovered by Newton, were subsequently to be stated by him with greater force and conciseness. The laws were of primary importance, because they afforded a new and correct way of considering not only the underlying reasons for the motions of the planets, but of all mechanical problems involving matter and motion. Aside from the three great laws of planetary motion established by Kepler as the result of many observations, the most important lesson taught by him, and one that was readily learned by Newton, was that the motions of the planets were not to be attributed to the influence of mere geometrical points, such as the centers of the old epicycles, but to the actual presence of other bodies. Kepler suggested, in particular, that the planets might be considered as connected with the Sun, and therefore as sharing to some extent the Sun's motion of revolution. From the Sun emanated that special kind of influence which he assumed. Yet, while Kepler considered the Sun as the source of this hypothetical force, he believed in a more general gravity or attraction between bodies. He was unfortunate enough, however, to conceive of it diminishing simply in proportion to the distance between the two bodies, a mathematical impossibility, as was demonstrated by Newton. This is the more surprising as he had demonstrated that the intensity of light was reciprocally proportional to the surface over which it was spread, and that it varied inversely as the square of the distance from the luminous body. It was also unfortunate that, while Kepler's ideas of the nature of gravity were sound and accurate in many respects, they bore no particular logical connection either one with another or with his theory of planetary motion. They are, however, worthy of comment as indicating the situation before Newton took these and other speculative ideas and the three isolated laws of planetary motion and bound them together into one beautiful doctrine which must underlie all astronomical science. Kepler, in his work Commentaries on the Motions of Mars, definitely states that gravity is a corporal affection, reciprocal between two bodies of the same kind, which tends, like the action of a magnet, to bring them together. When the earth attracts a stone, the stone at the same time attracts the earth, but by a force feebler in proportion as it contains a smaller quantity of matter. He then proceeds to state that if the Moon and Earth were not retained in their respective orders by an animal or other equivalent force, the Earth would mount toward the Moon 1/54th part of the interval which separates the two, and the Moon would descend the 53 remaining parts, supposing it to have the same density. This idea of gravity, according to Kepler, was indeed general and served to explain the cause of the tides, as is clearly indicated in the following passage. If the Earth ceased to attract its waters, the whole sea would mount up and unite itself with the Moon. The sphere of the attracting force of the Moon extends even to the Earth and draws the waters towards the torrid zone, so that they rise to the point which is the Moon in the zenith. After Kepler had promulgated his famous laws of planetary motion, many minds independently conceived a force to account for the remarkable uniformity of that motion. Thus the idea occurred to Robert Hooke, to Christopher Wren, and perhaps to Edmund Halley, who was Newton's most intimate friend and who probably did more than any other man of his time to popularize the idea of universal gravitation. It remained for the towering genius of Sir Isaac Newton (1643 1727) to formulate into a mathematical law of gravitation the effect of that universal force with which every schoolboy is now acquainted. The honor of having anticipated Newton was claimed by Hooke, and the two entered into an acrimonious controversy. Hooke never brought forward convincing proof of his claims. So far as Newton is concerned, the great merit of his work lay not so much in conceiving the law of gravitation as in his brilliant demonstration of its truth. Starting with Kepler's laws of planetary motion, he showed not only that they were true, which was hardly a task of merit after Kepler had considered the observations of Tycho Brahe and all other astronomers whose recorded observations would throw any light on the subject, but why those laws were true, and why no other laws could have accounted for the conditions actually observed in the motion of the planets. And, furthermore, underlying these famous planetary laws he discovered must be the attraction of gravitation. By a mathematical analysis unrivaled in the history of astronomy he proved his theorem completely. Not only did he suggest, as did Kepler, that the power of attraction resided in the Sun, but he proved mathematically that as a necessary consequence of that attraction every planet must revolve in an elliptical orbit around the Sun, having the Sun as one focus, and that the radius of the planet's orbit must sweep over equal areas in equal times, and that in comparing the movements of two planets it is necessary that the squares of the periodic times be proportional to the cubes of the mean distances. These facts were discovered by Kepler. They were explained by Newton, with the aid of the powerful and celebrated mathematical reasoning which he had created. The explanation was the law of gravitation. It occurred to Newton that if a diagram of the path of the Moon for any given period, say 1 minute, be made, it would be found that the Moon departs from a straight line during that period by a measurable distance. In other words, the Moon has been virtually pulled toward the Earth by an amount that is represented by the difference between its actual position at the end of the minute and the position it would occupy if it had moved in a straight line, which according to Galileo's law of motion it should follow unless some external force deflected it. By measuring the amount of deflection he had a basis for determining the amount of the deflecting force. This deflection Newton found by his calculation to be 13 feet. Obviously the force that acted on the Moon made it fall toward the Earth a distance of 13 feet during the first minute of its fall. Galileo had shown that the rapidity of a body's fall to the Earth increased at a uniform rate, what is now termed the acceleration of gravity. In other words, the higher the starting point of the fall, the greater would be the final velocity. Hence, the amount of the attracting force is in some way related to the distance between the two bodies, a relation which Newton expressed by stating that the falling body is attracted to the Earth by a force which varies inversely as the square of the distance between them. If the attracting force then varies inversely as the square of the distance, would the Moon drop toward the Earth at the calculated rate of 13 feet in the first minute? That was the problem which presented itself to Newton. The mathematical solution was simple, based as it was on a comparison of the Moon's distance with the length of the Earth's radius. Unfortunately there were no accurate dimensions of the Earth available when Newton made his first calculation in 1666. Hence he found, on the basis of the erroneous data at his disposal, that the Moon fell toward the Earth 15 instead of 13 feet during the first minute, a discrepancy so great that he dismissed the matter from his mind. When in 1682 his attention was called to a new and apparently accurate measurement of a degree of the Earth's meridian made by the French astronomer Picard, he attacked the problem anew. As he proceeded with his computation it became more and more certain that this time the result harmonized with the observed facts. So completely was he overwhelmed that he was forced to ask a friend to complete the simple calculation. When the computation was ended it was known that the force which causes bodies to fall to the Earth extends outward to the Moon, and that by reason of this force the Moon circles around the Earth. It required but a slight stretch of the imagination to assume that a force which can span the distance between the Earth and the Moon may also span the distance from the Sun to the Earth and the other members of the solar system. That such is really the case, Newton proved by a mathematical calculation of the orbital motions of Jupiter's satellites and of the various planets. These discoveries and fundamental principles, enunciated by Newton, were elaborated with great exactness in his Principia, and the section which discusses the motions of the Moon, confessedly one of the most difficult problems in celestial mechanics, has been termed by Sir George Airy the greatest chapter on physical science ever written. That it has stood the test of time is demonstrated by the fact that Newton's results have scarcely been extended in the centuries which have elapsed since their publication. The entire work is a marvel of exact mathematical reasoning by the greatest genius the world has ever produced, according to Lagrange's estimate of Newton's intellectual powers. Galileo had experimentally shown before Newton that the rate at which two bodies fall to the ground from equal heights is independent of their weights. A mass of gold and a mass of lead, although of unequal weight, reach the earth at the same time, if dropped simultaneously from the same height. Newton repeated the experiment very exactly. He realized as a result that weight, gravitation, is constant. Because a pound of lead weighs less than 2 pounds of lead, in other words is attracted with one half the force, merely for the reason that it contains less matter, he was forced to the conclusion that gravitation is dependent upon quantity of matter as well as distance. Thus he introduced the very difficult conception of mass as distinguished from weight, or the force of attraction exerted on it by the earth. The former, of course, is absolute and constant, but the latter varies with the position of the material in question on the earth's surface or elsewhere in the universe. If the mass of Venus is 7 times that of Mars, then the force with which the Sun attracts Venus is 7 times as great as that with which it would attract Mars if placed at the same distance. And therefore also the force with which Venus attracts the Sun is 7 times as great as that with which Mars would attract the Sun if at an equal distance from it. Hence, in all cases of attraction, the force is proportional not only to the mass of the attracted body, but also to that of the attracting body, as well as being inversely proportional to the square of the distance. Gravitation thus appears no longer as a property peculiar to the central body of a revolving system, but as belonging to a planet in just the same way as to the Sun, and to the Moon, or to a stone in just the same way as to the Earth. Moreover, the fact that separate bodies on the surface of the Earth are attracted by the Earth and therefore in turn attract it, suggests that this power of attracting other bodies, which the celestial bodies are shown to possess, does not belong to each celestial body as a whole, but to the separate particles of which it is composed, so that, for example, the force with which Jupiter and the Sun attract each other is the result of compounding the forces with which the separate particles making up Jupiter attract the separate particles making up the Sun. Thus is suggested finally the law of gravitation in its most general form. Every particle of matter attracts every other particle with a force proportional to the mass of each and inversely proportional to the square of the distance between them. When Newton completed his Principia, astronomy became in the fullest sense an exact science. Given the positions, velocities, and motions of the Sun, Earth, Moon, and other planets, then the manner in which they interact on one another can be learned, and even their form and dimensions determined. In short, astronomy, from a more or less mystical science, became in earnest a mathematical science. When the motions and orbits of heavenly bodies were once observed, the positions of these bodies could be computed for future epochs. In his Principia, Newton confines himself to the demonstration of the laws of gravitation. He says nothing about the means by which bodies are made to gravitate toward each other. His mind did not rest at this point. He felt that gravitation itself must be capable of being explained. It is known that he even suggested an explanation depending on the action of an ethereal medium pervading space. But with that wise moderation which is characteristic of all his investigations, he distinguished such speculations from what he had established by observation and demonstration, and excluded from his Principia all mention of the cause of gravitation, reserving his thoughts on this subject for the Queries printed at the end of his Optics. The attempts which have been made since the time of Newton to solve this difficult question are few in number, and have not yet led to any well established result. End of Section 6.
Section 7 of the Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Edward Labonte. The Science History of the Universe, Volume 1, edited by Francis Rolt-Wheeler. Astronomy, Chapter 6, The Solar System, Planetary Distances. To the ancients, as well as to the moderns, the sun and the moon appeared not only the largest, but the most important of all the celestial bodies. With the sun and moon, 5 other conspicuous spheres eventually were linked, spheres distinguished by reason of their regular motions. These orbs, Mercury, Venus, Mars, Jupiter, and Saturn, were named planets, or wanderers, to distinguish them from the fixed stars. Venus, familiar as the evening star or the morning star, was discovered, it is claimed, by Pythagoras in the 6th century BC, but even in the poems of Homer there are references to both stars without any indication of their identity. Jupiter, Venus, Mars, and Saturn ranking with the brightest of the stars, and Mercury occasionally seen near the horizon just after sunset or before sunrise. All were known to the ancients. A study of their movements naturally led to the obvious conclusion that all these moving stars or planets were related in some way, and that the motion of one was more or less dependent on the motions of the others. Hence it may be asserted that the ancient history of astronomy begins with the system of planets that revolve around the sun. What is the nature of these planets? Obviously, they are not all alike in size or distance. Even to the naked eye, their appearance seems to reveal conditions that need explanation. Early observation and study revealed the fact that the planets occupied a section of the heavens where there were no so-called fixed stars. But later observation also revealed that associated with the planets are a number of smaller bodies of much the same nature, known as planetoids or asteroids, which, with a single exception, occupy the zone of the heavens between Mars and Jupiter. Lastly, there are a large number of temporary visitors to this solar system, known as the comets. They plunge in from space, sweep around the sun, and drift away by various paths or orbits, most of them never to return. Planets, satellites, planetoids, and comets comprise the solar system. Vast and marvelously complete as that system is, it must be admitted that it is but a part of the great universe. It may be, as there is some reason to suppose, that this solar system is but one of many similar systems scattered throughout the universe, and that each of these, including that in which the Earth is situate, is in turn wheeling about some central orb inexpressibly distant. The solar system to which the Earth belongs is merely a type and not a unique example of planetary order. The intellectual rise in astronomy is nowhere more clearly revealed than in the history of man's conception of the solar system. Perhaps the first inquiry that must have flashed across the mind of a thinking Chaldean or Greek concerned itself with the distances of the heavenly bodies. How far away are the planets? How is their distance measured? The second question concerned itself with their motions. Whither do they drift and why? Around these questions cluster a group of vague guesses, fruitless speculations and poetic fancies, from which at last a scientific method was evolved for measuring planetary distances and accounting for planetary movements. It was not until comparatively late in astronomical history that means were devised for ascertaining the physical condition of each planet. The distances of the planets, small as they seem in comparison with sidereal measurements, are felt to be immense. Using only round numbers, which are sufficiently accurate for the present purpose, the planet Neptune, the outermost known member of our system, is 2,800,000,000 miles from the Sun. In a cord 28 feet long, each single foot will represent 100 million miles. On such a scale, a map of the United States could not be seen without the aid of a microscope. Suppose a bead were placed at each end of this line, one representing the Sun, the other Neptune. Between the two, other beads will represent the other planets. One nearly 4 inches from that representing the Sun will be Mercury, another at about 7 inches, Venus, a third at 11 inches, the Earth, a fourth at 17 inches, Mars, a fifth at about 5 feet, Jupiter, a sixth at 9 feet, Saturn, a seventh at 18 feet, Uranus, and an eighth, Neptune, at the end. The mean distances of the planets from the Sun are as follows: Mercury, 36 million miles; Venus, 67,200,000 miles; Earth, 92,900,000 miles; Mars, 141,500,000 miles; Jupiter, 483,300,000 miles; Saturn, 886 million miles; Uranus, 1,781,900,000 miles; Neptune, 2,791,600,000 miles. Attempts to measure some of these distances approximately are found in early times. The idea that some of the planets must be nearer the Earth than others must have been suggested by eclipses and occultations, in other words, passage of the Moon over the Sun and over a planet or fixed star. No direct means being available for determining the distance, rapidity of motion anciently was employed as a test of probable nearness. The stars being seen above, it was but natural to think of the most distant celestial bodies as the highest, and accordingly Saturn, Jupiter, and Mars, being beyond the Sun, were called superior planets, as distinguished from the two inferior planets, Venus and Mercury. Uranus and Neptune are modern additions to the solar system and could not have been included in the hypothesis. Aristotle, 384 to 322 BC, for example, arrived at the conclusion that the planets are farther off than the Sun and Moon as the result of an occultation of Mars by the Moon, and as the result of similar observations made in the case of other planets by the Egyptians and Babylonians. Ptolemy, 2nd century A.D., although far more original and daring in his astronomical conceptions than Aristotle, was able to add but little toward a solution of the problem. He expressly states that he had no means of estimating numerically the distances of the planets, or even of knowing the order of the distance of the several planets. He followed tradition in conjecturally accepting rapidity of motion as a test of nearness, and placed Mars, Jupiter, Saturn, which performed the circuit of the celestial sphere in about 2, 12, and 29 years respectively, beyond the Sun in that order, as Venus and Mercury accompany the Sun and may therefore be regarded as on the average performing their revolutions in a year. The test, to some extent, failed in their case, but Ptolemy again accepted the opinion of the ancient mathematicians, probably the Chaldeans, that Mercury and Venus lie between the Sun and Moon, Mercury being the nearer to the Earth. Copernicus gave the first glimpse of the truth. To quote Berry in his Short History of Astronomy, quote, "From the fact that Venus and Mercury were never seen very far from the Sun, it could be inferred that their paths were nearer to the Sun than that of the Earth, Mercury being the nearer to the Sun of the two, because never seen so far from it in the sky as Venus, the other three planets being seen at times in a direction opposite to that of the Sun must necessarily revolve round the Sun in orbits larger than that of the Earth, a view confirmed by the fact that they were brightest when opposite the Sun, in which positions they would be nearest to us. The order of their respective distances from the Sun could be at once inferred from the disturbing effects produced on their apparent motions by the motion of the Earth. Saturn, being least affected, must on the whole be farthest from the Earth, Jupiter next, and Mars next. The Earth thus became one of 6 planets revolving round the Sun. the order of distance, Mercury, Venus, Earth, Mars, Jupiter, Saturn, being also in accordance with the rates of motion round the Sun, Mercury performing its revolution most rapidly, in about 88 days, Saturn most slowly, in about 30 years." Unquote. It was not until John Kepler, 1571 to 1630, published his Epitome of the Copernican Astronomy, his Harmony of the World, and a treatise on comets, that astronomers were given a definite formula which enabled them to determine planetary distances with any exactitude. Kepler's speculative and mystic temperament led him constantly to search for relations between the various numerical quantities occurring in the solar system. By a happy inspiration, he tried to discover a relation between the sizes of the orbits of the various planets and their times of revolution round the Sun. After a number of unsuccessful attempts, he discovered a simple and important relation commonly known as Kepler's third law. Quote, "The squares of the times of revolution of any two planets, including the Earth, about the Sun are proportional to the cubes of their mean distances from the Sun." Unquote. In other words, given the periods, there is need only to find the interval between any two of them in order to infer at once the distance separating them all from one another and from the Sun. Here was the plan. What was next to be discovered was the scale upon which the plan was to be drawn. There must be first a trustworthy measure of the distance of a single planet from the Sun, the Earth for example, and the problem would be solved. How is this measure to be obtained? Sir Robert Ball, in his Story of the Heavens, gives this simple example for partial explanation. Quote, "Stand near a window where you can look at buildings, or at any distant object. Place on the glass a thin strip of paper vertically in the middle of one of the panes. Close the right eye and note with the left eye the position of the strip of paper relatively to the objects in the background. Then, while still remaining in the same position, close the left eye and again observe the position of the strip of paper with the right eye. You will find that the position of the paper on the background has changed. Move closer to the window and repeat the observation, and you find that the apparent displacement of the strip increases. Move away from the window and the displacement decreases. Move to the other side of the room, the displacement is much less, though probably still visible. We thus see that the change in the apparent place of the strip of paper as viewed with the right eye or the left eye varies in amount as the distance changes. But it varies in the opposite way to the distance, for as either becomes greater, the other becomes less. We can thus associate with each particular distance a corresponding particular displacement. From this, it will be easy to infer that if we have the means of measuring the amount of displacement, then we have the means of calculating the distance from the observer to the window. It is this principle, applied on a gigantic scale, which enables us to measure the distances of the heavenly bodies. Look, for instance, at the planet Venus. Let this correspond to the strip of paper, and let the Sun, on which Venus is seen in the act of transit, be the background. Instead of the two eyes of the observer, we now place two observatories in distant regions of the Earth. We look at Venus from one observatory. We also look at it from the other. We measure the amount of displacement, and from that we calculate the distance of the planet. All depends then on the means which we have of measuring the displacement of Venus as viewed from the two different stations." Unquote. Two observers standing upon the Earth must be some thousands of miles apart in order to see the position of the Moon altered with regard to the starry background to obtain the necessary data upon which to ground their calculations. The change of position thus offered by one side of the Earth's surface at a time is not sufficient, however, to displace any but the nearest celestial bodies. When there is occasion to go farther afield, a greater change of place must be sought. This can be obtained as a consequence of the Earth's movement around the Sun. Observations taken several days apart will show the effect of the Earth's change of place during the interval upon the positions of the other bodies in our system. But when the depths of space beyond are to be sounded, and an effort is made to reach out for the purpose of measuring the distance of the nearest star, the utmost change of place is necessitated. This results from the long journey of many millions of miles which the Earth performs around the Sun during the course of each year. Still, even this last change of place, great as it seems in comparison with terrestrial measurements, is insufficient to show anything more than the tiniest displacements in a paltry 43 out of the entire host of stars. It is thus readily realized with what an enormous disadvantage the ancients coped. The measuring instruments at their command were utterly inadequate to detect such small displacements. It was reserved for the telescope to reveal them, and even then it required the great telescopes of recent times to show the slight changes in the position of the nearer stars, which were caused by the Earth's being at one time at one end of its orbit, and some 6 months later at the other end, stations separated by a gulf of about 186 million miles. It was from an opposition of Mars observed in 1672 by John Richter, unknown date of birth to 1696, at Cayenne in concert with Giovanni Domenici Cassini at Paris, that the first scientific estimate of the Sun's distance was derived. The Sun appeared to be nearly 87 million miles away. John Flamsteed, 1646 to 1720, the first Astronomer Royal of England, deduced 81,700,000 from his independent observations of the same occurrence. John Piccard's, 1620 to 1682, later result was just one half Flamsteed's, 41 million. Philippe de la Hire thought that the Earth must be separated from the Sun by at least 136 million miles. The transits of Venus in 1761 and 1769 were employed after other attempts had been made to measure the Sun's distance. The transit of 1769 is of particular interest, not only for a fairly good determination of the Sun's distance, but also for the reason that the celebrated Captain Cook was commissioned to sail to Otaheite for the purpose of witnessing the transit of Venus. At Otaheite on June 3rd, the phenomenon was carefully observed and measured. Simultaneously with these observations, others were obtained in Europe and elsewhere. From a combination of all the observations, an approximate knowledge of the Sun's distance was gained. The most complete discussion of these observations did not, however, take place for some time. It was not until the year 1824 that the illustrious Johann Franz Encke computed the distance of the Sun and gave as the definite result 95 million miles. Later, Urbain Jean-Joseph Le Verrier, 1870, reduced the estimate to 91,320,000 miles, which held good until Professor Simon Newcomb in 1882 gave the figure 92,475,000 miles. In 1900, nearly all the observatories of the world, under the direction of Maurice Loewy of the French Academy of Science, began a new computation which will lead to more exact results. The old problem of measuring a planet's distance from the Sun is not yet completely solved. If Sir David Gill's plan of basing a new set of calculations on the opposition of Eros in 1931 is carried into execution, the Sun's distance will be ascertained to within 10,000 miles. Present knowledge declares the distance of the planets from the Sun with an error not exceeding 1/50th of 1%. End of section 7.
Section 8 of The Science, History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Fred Abood. The Science, History of the Universe, Volume 1. Edited by Francis Rolt-Wheeler. Astronomy. Chapter 7. The Solar System. The Motions of the Planets. The motions of the planets also formed the basis for archaic theorizing. That the planets move, the ancients were fully aware, for the very word planet means wanderer. The strip of the celestial sphere through which moved the sun, the moon, and the 5 planets known to the ancients, Mercury, Venus, Mars, Jupiter, and Saturn, was called the zodiac, because the constellations in it were named after living things, with one exception. The zodiac was divided into 12 equal parts, the signs of the zodiac, through one of which the sun passed every month, so that its position could be roughly given by stating in what sign it was. The stars in each sign were formed into a constellation, the sign and the constellation each receiving the same name. The relative movements of the planets, as the ancients conceived them, are thus summarized by Berry. In Pythagoras occurs perhaps for the first time an idea which had an extremely important influence on ancient and medieval astronomy. Not only were the stars supposed to be attached to a crystal sphere, which revolved daily on an axis through the Earth, but each of the 7 planets, the sun and moon being included, moved on a sphere of its own. The distances of these spheres from the Earth were fixed in accordance with certain speculative notions of Pythagoras as to numbers and music. Hence, the spheres as they revolved produced harmonious sounds, which specially gifted persons might at times hear. This is the origin of the idea of the music of the spheres, which recurs continually in medieval speculation and is found occasionally in modern literature. At a later stage, these spheres of Pythagoras were developed into a scientific representation of the motions of the celestial bodies, which remained the basis of astronomy till the time of Kepler. Philolaus, the Pythagorean, who lived about a century after his master, introduced for the first time the idea of the motion of the Earth. He appears to have regarded the Earth, as well as the sun, moon, and 5 planets, as revolving around some central fire, the Earth rotating on its own axis as it revolved, apparently in order to ensure that the central fire should always remain invisible to the inhabitants of the known part of the Earth. Although pure fancy, the idea of Philolaus was a valuable contribution to astronomical thought. Despite the immense influence of the Pythagoreans, most Greeks shared Plato's idea that any careful study of celestial motions was degrading rather than elevating, for the whole subject smacked too much of the unaesthetic section of geometry. Still, Plato, 429 to 347 BC, did give a short account of the celestial bodies, according to which the sun, moon, planets, and fixed stars revolve on 8 concentric and closely fitting wheels or circles around an axis passing through the Earth. This idea of Plato's was more or less followed by later philosophers. Thus, Eudoxius of Cnidus, 409 to 356 BC, attempted to explain the more obvious peculiarities of planetary motion by means of a combination of uniform circular motions. The celestial motions were to some extent explained by means of a system of 27 spheres, 1 for the stars, 6 for the sun and moon, 20 for the planets. There is no clear evidence that Eudoxius made any serious attempt to arrange either the size or the time of revolution of the spheres so as to produce a precise agreement with the observed motion of the celestial bodies, though he knew with considerable accuracy the time required by each planet to return to the same position with respect to the Sun. In other words, his scheme represented the celestial motions qualitatively but not quantitatively. Aristotle adopted this scheme of Eudoxus, but needlessly complicated it by treating the spheres as material bodies and added 22 more spheres, thus making 56 in all. He argues against the possibility of the Earth's revolving around the Sun, on the ground that there ought to be a corresponding apparent motion of the stars, an objection finally disposed of only during the 19th century, when it was discovered that this motion can be seen only in a few cases because of the unutterably great distance of the stars. No substantial advance can be noted until Hipparchus, 160 to 125 BC, made an extensive series of observations with all the accuracy that his instruments would permit, and critically made use of old observations for comparison with later ones, so as to discover astronomical changes too slow to be detected in a single lifetime, an essentially modern method. He systematically employed a geometrical scheme, that of eccentrics and epicycles, for the representations of the motions of the Sun and the Moon, a mode suggested in substance by Apollonius of Perga, who flourished in the 3rd century BC. The great services rendered to astronomy by Hipparchus can hardly be better expressed than in the words of the great French historian of astronomy, Delambre, who is in general no lenient critic. When we consider all that Hipparchus invented or perfected, and reflect upon the number of his works and the mass of calculations which they imply, we must regard him as one of the most astonishing men of antiquity, and as the greatest of all in the sciences which are not purely speculative, and which require a combination of geometrical knowledge with a knowledge of phenomena to be observed only by diligent attention and refined instruments. The last great name encountered in tracing the record of changing conceptions of planetary motions is that of Ptolemy, 100 to 170 AD, whose reputation rests on his Almagest, which may be regarded as the astronomical gospel of the Middle Ages. Hipparchus, as we have seen, found the current representations of the planetary motions inaccurate and collected a number of new observations. These, with fresh observations of his own, Ptolemy employed in order to construct an improved planetary system. Following the idea of Hipparchus, Ptolemy thought that the Sun and Moon moved in circular orbits around the Earth as a center. Ptolemy's chief work was to expand the system of epicycles so that it could explain discrepancies between theory and observation, discrepancies overlooked or ignored by Hipparchus. The deviations of the planets from the ecliptic, for example, were accounted for by tilting up the planes of the epicycles. Thus, with the aid of the system of Hipparchus, supplemented with his own idea of tilting epicycles, he worked out with great care and labor the motions of the planets. Although the Hipparchian Ptolemaic doctrine was framed on an extravagant estimate of the importance of the Earth in the scheme of the heavens, yet it must be admitted that the apparent movements of the celestial bodies were thus accounted for with considerable accuracy. For 14 centuries, the Almagest was regarded as the final authority on all questions of astronomy, and it may be considered as the loftiest piece of calculation appertaining to the ancient world. End of section 8.
Section 9 of the Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Edward Labonte. The Science History of the Universe, Volume 1, edited by Francis Rolt-Wheeler, Astronomy, Chapter 8, The Solar System, Modern Investigation, Part 1. The Ptolemaic system of astronomy was discredited only at an epoch nearly simultaneous with that of the discovery of the New World by Columbus. The true arrangement of the solar system was then expounded by Nicholas Copernicus, 1473 to 1543, in the great work De Revolutionibus, to which he devoted his life. The first principle established by these labors showed the diurnal movement of the heavens to be due to the rotation of the earth on its axis. Copernicus pointed out the fundamental difference between real motions and apparent motions. He proved that the appearances presented in the daily rising and setting of the sun and the stars could be accounted for by the supposition that the earth rotated just as satisfactorily as by the more cumbrous supposition of Hipparchus and Ptolemy. He showed moreover that if the ancient supposition were true, the stars must have an almost infinite velocity, and declared that the rotation of the entire universe around the earth was clearly preposterous. The second great principle, which has conferred immortal glory on Copernicus, assigned to the earth its true position in the universe. Copernicus transferred the center, about which all the planets revolve, from the earth to the sun, and he established the somewhat crushing truth that the earth is merely a planet pursuing a track between the paths of Venus and of Mars, and subordinated, like all the other planets, to the supreme sway of the sun. This great revolution swept from astronomy those distorted views of the earth's importance which arose, perhaps not unnaturally, from the fact that the observers chanced to live on this particular planet. Whether the actual services rendered by Copernicus are commensurate with his fame may be doubted. He labored under the weight of an ecclesiastical tradition that could not be abandoned without some risk. He was a bold man indeed, who dared to overthrow or even to question orthodoxy, and to diminish the earth's overshadowing importance in the solar system. The Copernican system was not flawless either in theory or logic, and many objections could be made to it, particularly by an astronomer who had observed and studied the movements of the heavenly bodies. After the example of the ancients, Copernicus assumed as an axiom the uniform circular motion of the planets, and as the only motions which are observed are in a state of incessant variation, he was obliged, in order to explain the inequalities, to suppose a different center for each of the orbits. The sun was placed within the orbit of each of the planets, but not in the center of any of them. In other words, he still adhered to a system of epicycles. Consequently, the sun performed no other office than to distribute light and heat. Excluded from any influence on the system, the sun became a stranger to all the motions. The fixed stars were alleged to be stationary, and it was necessary to suppose that they were almost infinitely distant, inasmuch as they always seemed to preserve the same position when viewed from the opposite sides of the Earth's orbit. While various astronomers showed some disposition to accept the Copernican teaching, most of them were bitterly opposed to it on ecclesiastical, traditionary, and scientific grounds. Tycho Brahe, 1546 to 1601, was the most distinguished of these opponents. Being an indefatigable observer and practically the first to realize the value of continuous observation, he enriched astronomy by a star catalogue and studies of the movements of the other heavenly bodies. Tycho accepted the Copernican conception of a central sun, but rejected the idea that the earth moved. Thus he sought to effect a compromise between the Ptolemaic and Copernican systems. It was the study of a comet in 1577 that led Tycho to formulate his ideas of the solar system. He believed that the comet X, as shown in the accompanying diagram, was revolving around the sun at a distance greater than that of Venus, and assumed that both the sun C and the earth A were centers of revolving systems. the 5 planets revolving around the Sun and the entire system in turn moving around the Earth. This incorrect proposition, which was one of the least of Tycho Brahe's contributions to astronomical science, is significant, showing as it does how difficult it was for the principles of Copernicus firmly to establish themselves and planetary motion to be explained satisfactorily. Whatever Tycho may have thought of the Copernican system, his contemporary Galileo, 1564 to 1642, was willing to accept it. It has been shown how Galileo, with the telescope of his invention, was able to extend astronomical science and to introduce new methods of observation, which came naturally to one who was a leader in the experimental science of his time. But even before his work with the telescope, Galileo had adopted the astronomical views of Copernicus and collected arguments for their support. He was able in 1604 to confirm the discovery of Tycho Brahe that changes take place in the heavens beyond the planets, and that there was an important region beyond the Earth and its immediate surroundings. As was but natural, the use of the telescope broadened Galileo's horizon, and true scientist that he was, he immediately brought to bear his new discoveries on the fundamental conceptions. Thus his discovery of the satellites revolving around Jupiter as the planets themselves revolved around the Sun not only rendered necessary the explanation of these new bodies, but dealt a serious blow to the infallibility of Aristotle and Ptolemy, neither of whom had any idea of the existence of these satellites. Further support was given to the Copernican theory by the ocular demonstration of these satellites revolving around Jupiter and not dropping behind, just as the Moon was required to move around the Earth, a mechanical difficulty brought forward by the opponents of the Copernican idea. As Galileo developed his astronomical ideas and discoveries, he naturally came into conflict with ecclesiastical authority, and there began the unfortunate controversy as to the relative validity in scientific matters of observation and reasoning on the one hand, and the authority of the Church and Bible on the other. Controversies such as this were conspicuous in the latter part of Galileo's life. They culminated in his famous trial and formal abjuration of his alleged errors, and in his conviction, quote, of believing and holding the doctrines false and contrary to the holy and divine scriptures, that the sun is the center of the world, and that it does not move from east to west, and that the earth does move and is not the center of the world. Also that an opinion can be held and supported as probable after it has been declared and decreed contrary to holy scriptures, unquote. Despite Galileo's abjuration, his general attitude toward the Church and Bible is contained in his approval of the saying of Cardinal Baronius, quote, that the intention of the Holy Ghost is to teach us not how the heavens go, but how to go to heaven, unquote. His attempts to explain and demonstrate the Copernican system in his great astronomical treatise, Dialogue on the Two Chief Systems of the World, the Ptolemaic and Copernican, led to his trial and conviction before the Inquisition. Kepler, another of Galileo's contemporaries, did more even than the great Italian to bring about a proper conception of the solar system and the motions of the planets. A student under Tycho, it was but natural that Kepler should have imbibed from his master a respect for systematic observation, regardless of the correctness or incorrectness of Copernican views. As a result, Kepler early adopted the Copernican doctrine, opposed though it was by his master. His observations led him to the conclusion, however, that even Copernicus had not revealed all the mysteries of planetary motion, and that the hypothetical circles in which the planets revolved around the sun, according to Copernicus, did not agree with the paths observed. Under the instruction of Tycho, Kepler addressed himself to the problems involved in the planet Mars, whose positions as seen in the sky were a combined result of its own motion and that of the Earth, as both move around the sun. Actual observation of the planet and the consideration of various geometrical theories that suggested themselves eventually led to the conception that the path of the planet must be some form of an oval. Finally, Kepler reached the conclusion that instead of being circular, the planet's motion must lie in the simple curve known as an ellipse. and formed by taking an oblique section of a cone. While the circle has but a single center, the ellipse depends for its form upon two fixed points, each of which is termed a focus. It can be drawn by using two pins stuck in a sheet of paper and by inserting a pencil within a loop of string that also includes the two pins. The curve may be traced by moving the pencil while the string is kept taut. It will be found that if the 2 points are kept close together, the curve approaches in form a circle, while if they are separated, the figure becomes elongated and possesses what the mathematicians term greater eccentricity. At any rate, every point on the curve is such that the sum of its distance from the two foci is always the same. Kepler found that the Sun was at one focus. When the planet was near that focus, it moved with greater velocity than when at the opposite part of its orbit. The speed of motion, however, was always proportional to the area swept out by a straight line from the Sun in equal intervals of time. In other words, there were formulated the now famous first and second laws of Kepler as follows. 1. The planet describes an ellipse, the Sun being in one focus. 2. The straight line joining the planet to the Sun sweeps out equal areas in any two equal intervals of time. Kepler not only established these laws for Mars, but immediately applied his principle to Earth, and then claimed, without proof however, in his Epitome of the Copernican Astronomy, that these two fundamental laws applied also to all the planets and to the motions of the Moon. Accompanying these two laws was the third already discussed, in which it is stated that the squares of the times of revolution of any two planets, including the Earth, about the Sun are proportional to the cubes of their mean distances from the Sun. It was the disclosure of these wonderfully simple relations that laid the foundation for the Newtonian law of gravitation. Contemporary judgment, of course, could not anticipate the culmination of a later generation. What it could understand was that the first law of Kepler attacked one of the most time-honored of metaphysical conceptions, the Aristotelian idea that the circle is the perfect figure, and that planetary motions, consequently, must be circular. Not even Copernicus had doubted the validity of this assumption. Kepler was too great a genius to rest content with the mere observation that the planets move in ellipses. Next, he desired to determine why they do so move. It remained for Isaac Newton, 1643 to 1727, to answer the question satisfactorily. Yet Kepler had a curious premonition of the law of gravitation. Quote, "Whereas the Ptolemaic system," unquote, comments Berry, quote, "required a number of motions round mere geometrical points, centers of epicycles or eccentrics, equants, etc., unoccupied by any real body, and many such motions were still required by Copernicus, Kepler's scheme of the solar system placed a real body, the Sun, at the most important point connected with the path of each planet, and dealt similarly with the Moon's motion round the Earth, and with that of the 4 satellites round Jupiter. Motions of revolution came, in fact, to be associated not with some central point, but with some central body, and it became therefore an inquiry of interest to ascertain if there were any connection between the motion and the central body. The property possessed by a magnet of attracting a piece of iron at some little distance from it suggested a possible analogy to Kepler, who had read with care and was evidently impressed by the treatise On the Magnet, De Magnete, published in 1600 by William Gilbert of Colchester, 1540 to 1603. He suggested that the planets might thus be regarded as sharing to some extent the Sun's own motion of revolution. In other words, a certain carrying virtue spread out from the Sun, with or like the rays of light and heat, and tried to carry the planets around the Sun. Kepler says himself in his Epitome, quote, "There is therefore a conflict between the carrying power of the Sun and the impotence or material sluggishness, inertia, of the planet. Each enjoys some measure of victory, for the former moves the planet from its position, and the latter frees the planet's body to some extent from the bonds in which it is thus held. but only to be captured again by another portion of this rotary virtue." Unquote. Thus is faintly indicated the great theory of gravitation which, as developed by Newton, was to supply a satisfactory explanation of planetary motion, and which is the underlying basis of all modern astronomy. Newton had become convinced that the attracting power of the Earth extended even to the Moon, and that the acceleration produced in any body, whether it be as distant as the Moon or close to the Earth, was inversely proportional to the square of the distance from the Earth's center, and also proportional to the mass of the body. Then he found that the motions of the planets could be explained by an attraction toward the Sun, which produced an acceleration inversely proportional to the square of the distance from the center of the Sun, not only in the same planet, in different parts of its path, but also in different planets. Again, it follows from this that the Sun attracts any planet with a force inversely proportional to the square of the distance of the planet from the Sun's center, and also proportional to the mass of the planet. Accordingly, if the Earth or Sun attracts a body, the body must exert a similar force on the Earth or the Sun, and gravitation is not only a property of the central body of a revolving system, but belongs to every planet in just the same way as to the Sun and to a moon, or to a stone, just as to the Earth. After Newton had established provisionally the law of gravitation and the laws of motion, it remained for him to prove that the observed motions of the planets agreed with those calculated. A situation of the greatest complexity, however, was relieved by the fact that the mass of even the largest planets is so very much less than that of the Sun that the motion of any single planet is affected but slightly by the others, and it may be assumed to be moving very nearly as it would if the other planets did not exist, due allowance being made subsequently for minor disturbances or perturbations produced in its path. One by one the various irregularities observed were explained, and the motion of the Moon and its various eccentricities were computed with accurate numerical results. End of section 9.
Section 10 of The Science, History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Science, History of the Universe, Volume 1, edited by Francis Rolt-Wheeler. Astronomy, Chapter 8, The Solar System, Part 2. For many years, the solar system remained in its fancied integrity. There was no change in the original 5 planets, and the number of satellites first discovered by Galileo and added to by subsequent observers had reached an apparent culmination when G.D. Cassini had detected the second pair of satellites of Saturn in 1684. Accordingly, when Herschel, following his custom of making a review of the heavens with each new telescope that he constructed, found March 13th, 1781, with a Newtonian telescope 7 feet in length, a small star which appeared so much larger than its companions and of such uncommon appearance, he suspected it to be a comet. Further study revealed that it was more than a comet and of far greater interest. When heedfully observed and its path calculated, it was found that no ordinary cometary orbit would in any way fit its motion. Anders Johann Lexell first recognized that Herschel's body was not a comet, but a new planet revolving around the Sun in a nearly circular path and at a distance about 19 times that of the Earth and nearly double that of Saturn. A vain attempt by Herschel to name the new planet after his royal patron George III, Georgium Sidus, finally resulted in the proposal and acceptance by British and continental astronomers alike of the name Uranus, which harmonized with the names of the other planets. This discovery was of especial interest, inasmuch as Johann Daniel Titius, a professor at Wittenberg, had pointed out the remarkable symmetry in the disposition of the planets. In a note published in 1772, he showed that the distance of the 6 known planets from the Sun could be represented with a close approach to accuracy by a certain series of numbers, increasing in the regular progression 0, 3, 6, 12, 24, 48, etc. Adding 4 to each number, the results would give the relative distances of the 6 known planets from the Sun. In applying this law, which does not hold good in the case of Neptune, it was found that the term of the series following that which corresponded with the orbit of Mars was not represented in the list of planets. Accordingly, Johann Elbert Bode, a German astronomer, assumed a hypothetical planet to take this place. When Uranus was discovered, its distance was found to fall but slightly short of perfect conformity with the law of Titius, and it stimulated the search for a new body, which, as will be seen in the chapter of the planetoids, proved to be the small planet Ceres. The study of Uranus, after its discovery by Herschel, furnished many discoveries to astronomers. Despite the most careful calculations of the movements of the planet through more than a century's observations, the conclusion was reached that considerable errors existed or that the planet was wandering from its course. In fact, these disturbances had aroused the interest of several mathematicians and astronomers, and a young English student, John Couch Adams, soon after his graduation from Cambridge, communicated in 1845 to the Astronomer Royal numerical estimates of the elements and orbits of the unknown planet, which he assumed was acting on Uranus and was the cause of the disturbances. In fact, he indicated the actual place in the heavens of the hypothetical planet. At practically the same time, a French astronomer, Urbain Leverrier, who had made a careful study of the solar system in response to a request from Dominique F.J. Arago, the head of the French observatory, prepared an elaborate memoir in which he demonstrated that only an exterior body could produce the disturbances observed, and that such a body must occupy a certain and determinate position in the zodiac. He also assigned the orbit of the disturbing body, indicating that it would be as visible and bright as a star of the 8th magnitude. In fact, he supplied data to Professor Galle of the Berlin Observatory, which enabled that astronomer to find in the heavens on September 23, 1846, within less than a degree of the spot indicated, an object with a measurable disk. A reasonably complete map of this portion of the sky, in which all the stars were noted, proved beyond question that the object was not a star, while its movement, as predicted, was ample confirmation of its planetary nature. Adams' work, which antedated that of Leverrier, had not received attention originally in Great Britain at the hands of the Astronomer Royal, but as the matter assumed importance, the Cambridge Observatory also participated in the search, and on September 29, 1846, the planet was seen again. Thus, Neptune was discovered. To show the rapidity of astronomical research in the 19th century, it may be remarked that it required but 17 days for the discovery of a satellite by Lassell with a 2-foot reflecting telescope. Astronomers have suspected the existence of still other planets, and the belief has been expressed that such a body exists nearer to the Sun than Mercury, which, as has been seen, enjoys the reputation of being the closest of all the planets to the central luminary. The average distance of Mercury from the Sun is about 36 million miles, so that there would be enough space for such a planet. Its peculiar position in close proximity to the Sun, however, would act against its being observed. A small luminous point in this position would be altogether invisible, even with the best modern telescope, while its setting and rising, simultaneous almost with those of the Sun, make it invisible at these times, even under the most favorable conditions. If this planet should pass across the Sun's disk, just as do Mercury and Venus, it would be seen. While from its size it would be much less of a spectacle than the 2 planets mentioned, it might be detected. Claims have been advanced by astronomers that they have seen such a transit of a small spot. The first suggestion of an intramercurial planet came from the distinguished French astronomer Leverrier, who in 1859 advanced such a hypothesis in an attempt to explain the movements of the planet Mercury. His theory involved a body of about the size of Mercury revolving at somewhat less than half its mean distance from the Sun, or at a greater distance if of less mass, and vice versa, whose motion in great part would explain the irregularities observed. In the same year, Dr. Lescarbault at Orgères maintained that he had observed such a body crossing the Sun's disk, and the name of Vulcan was bestowed upon it. Several astronomers claimed to have seen the new planet. Their observations were not well authenticated, and on the dates fixed for the probable transits, no trace of the planet could be found. The strongest test was the examination of the sky at the time of a solar eclipse, for then the light of the sun was cut off, and a strange body could be readily identified. Despite a careful watch at subsequent eclipses and an examination of photographic plates, only negative results have been obtained. Today, the belief that there is any body of considerable size within the orbit of Mercury is held only by a few astronomers and very guardedly stated. If the search for an intramercurial planet was unsuccessful, it has in no way deterred astronomers from endeavoring to find other unrecognized members of the solar system. Much interest has been aroused by a hypothetical ultra-Neptunian planet, which of course would be the furthest from the Sun of all the members of the solar system. The basis for such a hypothesis is the reduction of observations made of the positions and motions of Uranus and Neptune. Neptune has been under observation for only a small part of a revolution, so that data thus far obtained seemed to many astronomers insufficient for the purpose. Yet a number of astronomers have sought by calculation to prove the existence of such a planet. While their results are discordant, yet they indicate very closely the regions of the sky where search for the hypothetical body might be rewarded with success. Professor W. H. Pickering of Harvard in 1909 evolved a method for the discovery of the distant planet, a method which he first tested by application of the data available to Adams and Leverrier for the discovery of Neptune, and found that the method would succeed. Proceeding then with his hypothetical planet, which he termed O, he found that it was 51.9 times as far distant from the Sun as the Earth, though its mass was but twice that of this planet, and that it had a period of revolution of 373.5 years. The problem presented by Uranus, Neptune, and O, according to Professor Pickering, is quite the same as that of Mercury, Venus, and the Earth, which has been thoroughly studied, so that the relative motions are well understood. But in investigating the effect that such a hypothetical planet would have on the motion of Uranus, Professor A. Gallo recently arrived at the conclusion that there were indications pointing to the possibility of still another and more distant planet also exercising a perturbing influence. The results of his calculations and studies therefore indicate the possible existence of two ultra-Neptunian planets, one at a distance from the Sun equal to 44 times the Earth's mean distance, and having a mass of about 1/64,000th the mass of the Sun, the other having a distance 66 times that of the Earth, and a mass of about 1/14,000th that of the Sun. While these figures disagree with those of Professor Pickering, yet the position calculated for the second planet agrees quite closely with that of the Harvard astronomer. The problem is by no means solved. It is mentioned to show that a plausible case has been made for at least one ultra-Neptunian planet. After astronomers had definitively decided how far the planets and the Sun are situated from the Earth and how they move with respect to one another, they began to wonder if perhaps the whole solar system did not in turn revolve around some central orb. The possibility first occurred to Tobias Mayer, Jean Michel, and Joseph Jérôme Lefrançois Lalande, but the problem was not attacked with any degree of success until William Herschel in 1782 began to draw conclusions from his study of the Milky Way, and decided that the entire solar system was drifting toward the constellation Hercules. But Herschel's theory did not meet with general acceptance for many years. Other astronomers suggested various stars as possible central suns controlling the movement of our solar system, Thus, Mädler not only proposed that Alcyone, the principal star in the Pleiades, should be the central sun because of its situation at a point of neutralization of opposing tendencies and consequently at rest, but even went so far beyond the limits of astronomy as to declare that, quote, "Here was the seat of the Almighty, the mansion of the Eternal," end quote. It is hard even for science to quell the imagination and to confine an observer to facts. Mädler's theory was short-lived. Further study of the stars demonstrated the soundness of Herschel's views. When a modern telescope is turned toward the Milky Way, this white girdle of the celestial sphere is resolved into a vast number of stars, of which more than 140 million already have been counted on photographs. Each of these stars is a sun like that which governs the Earth, probably surrounded by planets like the Earth, and all these solar systems also are moving, many of them more swiftly than ours. It was inferred from Herschel's measurements of stellar positions, distances, and motions that the solar system was situated comparatively near the center of a universe shaped like a thin double convex lens. This universe was supposed to rotate as a unit about its center, with the result that the sun, comparatively near that center but absolutely at an immense distance from it, moved in a circle of dimensions so vast that since the discovery of its motion it had not deviated appreciably from a straight line, but had steadily directed its course toward the constellation Hercules. This simple scheme must now be abandoned, for it has been discovered by Professor J.C. Kapteyn, a Dutch astronomer, that the visible universe consists of two distant parts. The scientific imagination is compelled to picture two processions of stars, moving in paths which make an angle of 115 degrees with each other. One of these stellar streams moves 3 times as fast as the other. The sun forms a part of one of the streams and is at present at their intersection. Although it is known in a general way that the entire solar system is moving through space at the rate of 12 miles a second, the shape and size of the sun's orbit are utterly unknown. The changes of environment, accordingly, that will accompany the description of it defy conjecture. The actual course of the solar system is inclined at a small angle to the plane of the Milky Way. Presumably, it will become deflected, but perhaps not sufficiently to keep the system clear of entanglement with the galactic star throngs. In the present ignorance of their composition, no forecast of the results can be attempted. They are uncertain and exorbitantly remote. Hence, in a sense, the world knows where it is and in what direction it is moving. But what is the goal? When shall it be reached? And what will happen then? Or, in this crossing of the congested thoroughfares of the heavens, will the world be shattered by a collision and resolved into a glowing nebula? This has been the fate of many stars, of several within the period of human history, and of one, Nova Persei, within a few years, and witnessed in all its destructive detail by astronomers still living. End of Section 10. Recorded by Dan Longauger in Washington State.
Section 11 of the Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by K. Hand. The Science History of the Universe, Volume 1, edited by Francis Rolt-Wheeler. Astronomy. Chapter 9. The Sun, Eclipses, Sunspots and Aurorae, the Photosphere. Part 1. The preeminence of the sun among the celestial bodies and its obvious importance to the life of the world has given to it a unique place, not only in astronomy but in philosophy and religion. The rising of the sun and the light that it casts over the earth are distinctly symbolical of the conquest of light over darkness, or the triumph of truth over error, so that in many schemes of mythology the sun god assumes the highest rank and rules over the other elements, such as the moon, the rains and floods, and the stars. Of this there are abundant instances in all primitive religions. Among the Oriental nations, to whom we owe the idea of a flood from which the world emerged, the sun god reigned supreme. In Egypt, among the Chaldeans and Babylonians, and later among the Greeks and Romans, the sun held like sway. In Persia, sun worship was developed into a more formal religion, which survived for many years. After the mind of man had developed to a point where it was concerned with philosophical speculation rather than with the mysticism handed down by the priesthood, there came a desire to understand the relation of the sun to the earth and to the universe. Its motion across the sky was obvious, as well as its change of position from time to time. On this, as has been seen, various theories were founded. It was early realized that the sun described an annual path on the celestial sphere, which path is a great circle, and this great circle known as the ecliptic, because eclipses take place only when the moon is in or near it, is at an angle to the equator of the sphere. This angle is termed the obliquity of the ecliptic, and was measured by the Chinese, it is claimed, as early as 1100 B.C. with remarkable accuracy. Later, the same feat was claimed for Pythagoras or Anaximander in the 6th century B.C., both of whom probably derived their information from the Chaldeans or Egyptians. When the sun crosses the equator, the day is equal to the night, which occurs twice a year, at the vernal equinox about March 21st, and the autumnal equinox about September 23rd. When the sun is at its greatest distance from the equator on the north side, the time is known as the summer solstice, and when at its greatest distance on the south side, it is termed the winter solstice. The positions of these points in the heavens were also known to the early Chinese astronomers with considerable accuracy, while Anaximander, who supposed the sun to be of equal magnitude with the earth, used a gnomon, or vertical pillar, casting a shadow, to observe the solstices and equinoxes. Anaximenes is said to have believed that the sun was a mass of red-hot iron or of heated stone somewhat larger than the Peloponnesus. He looked upon the heavens as a vault of stones, prevented from falling by the rapidity of its circular motion, while the sun could not proceed beyond the tropics on account of a thick and dense atmosphere which compelled it to retrace its course. Later, Philolaus of Crotona, who was a disciple of Pythagoras and followed his master's teaching that the earth revolved about the sun, assumed that the sun was a disk of glass which reflected the light of the universe. Eudoxus of Cnidus, about 370 B.C., stated that the diameter of the sun was 9 times greater than that of the moon, which marked a triumph over the illusions of sense. About the time of Alexander, the great Pytheas, using the gnomon, determined the length of the shadows cast at the summer solstice in various countries. His observations are the most ancient of those preserved, after those made in China. The study of the sun was undertaken very systematically by Hipparchus, who discovered that the solar orbit was eccentric, and that the sun moved at different speeds at different parts of its journey. With his observational data, Hipparchus produced the first tables of the sun which are mentioned in astronomy. He was enabled to determine the difference between the solar day, or time as shown by the sun, and the time indicated by some such measuring device as the clepsydra, or water clock. The motion of the sun was also studied by Ptolemy. He compiled solar tables more extensive than those of Hipparchus, which were employed until Albategni, born 815, made a new compilation of greater accuracy, and which served as a connecting link between the astronomers of Alexandria and those of modern Europe. The obliquity of the ecliptic was constantly being studied. Ulu Beg, a Tartar prince and grandson of the great Tamerlane, at Samarcand, using a gnomon 100 feet in height, determined the obliquity of the ecliptic or precession of the equinoxes, and secured data for the construction of astronomical tables which were of considerable accuracy. The apparent motions of the sun furnished many difficult problems for the astronomer, since the observational data lacked accuracy on account of the absence of satisfactory instruments. Measuring angles by the shadow cast and positions in the sky by crude forms of angular measurement were not adequate for exact work. Not until the advent of the quadrant and the telescope with its various adjuncts was scientific measurement possible. But there were from time to time solar eclipses, of which a careful record was maintained, and which the ancient priests noted in connection with their calendar observations. These eclipses played a most important part in ancient astronomy. An eclipse of the Sun occurs when Earth, Moon, and Sun are in direct line at the time of new moon. As the latter lies between the Earth and the Sun, its dark body will pass across the Sun's disk, cutting off the direct illumination. If the Earth cuts off the sunlight from the Moon, there is a lunar eclipse. Solar eclipses are of three kinds: partial, annular, and total. In the first, the Moon, instead of passing directly between the Earth and the Sun, slips past on one side and cuts off from sight only a portion of the Sun's surface. In the annular eclipse, the Moon is centrally interposed between the Sun and the Earth, but falls short of the apparent size required to conceal the solar disk entirely. Consequently, at the height of obscuration, a bright ring is visible around the Moon. In a total eclipse, however, the Sun completely disappears behind the dark body of the Moon. The difference between a total and an annular eclipse depends upon the fact that the apparent diameters of the Sun and the Moon are so nearly equal as to preponderate alternately one over the other through the slight periodical changes in their respective distances from the Earth. It is the total eclipse that particularly arouses the attention of astronomers, for it cuts off entirely the light of the Sun, and in addition to enabling the observation of the various parts of its surface as it passes across its disk to be made, also makes it possible for an observer to see the stars and planets in the daytime, even if they are very near to the Sun. A total eclipse of the Sun is not visible on the entire Earth, but only along a comparatively narrow band, lying roughly from west to east and measuring about 165 miles in width. A partial eclipse is seen for about 2,000 miles on either side of this band, but otherwise the phenomenon is not visible on the Earth's surface. Chinese records going back over 4,000 years describe a solar eclipse which occurred during the 22nd century BC. That eclipse carried with it a distinct moral lesson. Two bibulous state astronomers, Ho and He, unfortunately happened to be drunk on the day of its occurrence, and hence incapable of supervising the performance of the required rites, which consisted in beating drums, shooting arrows, and other ceremonies intended to frighten away the mighty dragon who was about to swallow up the Lord of Day. Although the eclipse was only partial, nevertheless great confusion resulted, and Ho and He were put to death as a lesson to later astronomers. Another early record of a total eclipse comes from Babylon, 1063 BC. Several centuries later, Assyrian tablets record solar eclipses. Herodotus, Plutarch, and the Bible all refer to the phenomenon. Thus, one is enabled to determine with accuracy the time of historical events. Likewise, in the Anglo-Saxon chronicles, several notable eclipses are recorded. The Sun appears as a brilliant white body. Just as the Earth is enveloped by an atmosphere, so the Sun is surrounded by several layers of gaseous and vaporous matter, with the result that so far as an observer on the Earth is concerned, its nucleus is quite invisible. These layers are more or less transparent, just as the atmosphere of the Earth is transparent, so that the bright white body of the Sun is visible only through these various envelopes. This bright white portion is called the photosphere, and is the source of the light and heat which is radiated to the Earth. Here are found the sunspots distinctly seen with the telescope and even by the naked eye. Under the photosphere it may be that the more solid portions of the Sun are situated, but it is obvious that its surface consists of highly incandescent vapors above which is a smoke-like haze. Upon this rests the reversing layer, which is composed of glowing gases, but is cooler than the photosphere beneath. It has a thickness of between 500 and 1,000 miles and contains, as the spectroscope shows, many of the elements of which the Earth is composed, in the form of vapor. Above the reversing layer comes the chromosphere. The chromosphere is between 5,000 and 10,000 miles in thickness and is composed of glowing gases, chief among which is hydrogen. The chromosphere is a brilliant scarlet in hue, but the redness is entirely overpowered by the intense white light of the photosphere, which shows through from behind. The most interesting features of the chromosphere are the red prominences, which are the marks of violent agitation in its upper portions, and which are such a notable feature in total solar eclipses. After the chromosphere comes the corona, which is the outer envelope of the Sun, and consists of a halo of pearly white light of irregular outline, which fades away into the surrounding sky and extends outward for many millions of miles. The corona suffers so much from the brilliancy of the photosphere that it is only on the occasion of a total solar eclipse that it can be seen in all its remarkable beauty. As the photosphere, the reversing layer, and the chromosphere are all sources of light, the solar spectrum observed in spectroscopes is composed of the three separate spectra combined. For this reason, eclipses afford welcome opportunities for studying the Sun's surface. When the Moon completely covers the photosphere, its brilliant light is cut off, and the other features of the Sun can be examined visually, and, what is more important, spectroscopically and photographically. Thus, when the spectroscope is directed to the reversing layer during a total eclipse, the dark lines of the solar spectrum change into bright lines, or are reversed. But this reverse spectrum is a phenomenon of a moment only, and as the Moon progresses an altered spectrum is obtained. That of the chromosphere is of sufficiently long duration to permit an estimate of its depth and nature, and finally, when this is covered up, there is the corona, which has a distinct spectrum of its own, containing a strange line, the distinguishing green of which has not yet been identified with any element known upon the Earth. Modern conceptions of the Sun are due very largely to the use of the telescope, the spectroscope, and the spectroheliograph, especially the last two instruments. With this telescope, when the intense light of the Sun is properly reduced, it is possible to examine its surface and obtain a certain amount of information as to its nature, or to obtain photographs of that surface by very short exposures. But on the spectroscope and the spectroheliograph the astronomer depends for his knowledge of the constitution and composition of the greater center of the solar system. The development and nature of the spectroscope, as used in solar research, have been already discussed. But it is appropriate to add here a brief explanation of the spectroheliograph, for to its use is due not only a large part of present-day information of the prominences, but more recently an explanation of the sunspots themselves and the study of various features of the photosphere. The spectroheliograph was first devised in successful working form by Professor George E. Hale at Kenwood Observatory, Chicago, in 1889. The principle of this instrument is very simple, writes Professor Hale. Its object is to build up on a photographic plate a picture of the solar flames by recording side-by-side images of the bright spectral lines which characterize the luminous gases. In the first place, an image of the Sun is formed by a telescope on the slit of a spectroscope. The light of the Sun after transmission through the spectroscope is spread out into a long band of color, crossed by lines representing the various elements. At points where the slit of the spectroscope happens to intersect a gaseous prominence, the bright lines of hydrogen and helium may be seen extending from the base of the prominence to its outer boundary. If a series of such lines corresponding to different positions of the slit on the image of the prominence were registered side by side on a photographic plate, it is obvious that they would give a representation of the form of the prominence itself. To accomplish this result, it is necessary to cause the solar image to move at a uniform rate across the first slit of the spectroscope, and with the aid of a second slit, which occupies the place of the ordinary eyepiece of the spectroscope, to isolate one of the lines, permitting the light from this line and from no other portion of the spectrum to pass through the second slit to a photographic plate. If the plate be moved at the same speed with which the solar image passes across the first slit, an image of the prominence will be recorded upon it. The same method answers for the study of the sunspots and other features of the Sun's surface. As the result of telescopic, spectroscopic, and spectroheliographic observation, it is now known that the Sun's principal features are its sunspots, its photosphere, its chromosphere, and its corona. A sunspot when examined through a telescope consists of a dark central region called the umbra, into which long narrow filaments reach. The space occupied by these filaments is termed the penumbra. The darkness of the umbra is not absolute, but is relative to the more brilliant surface of the photosphere, and if observed alone would be far more brilliant than the most powerful arc light. These dark spots on the Sun were familiar objects in the days of pre-telescopic observation. But their importance to astronomy dates with their discovery in 1610 by Galileo with his telescope. The great Italian astronomer did not announce his discovery until May, 1612, by which time sunspots had been seen independently by Thomas Harriot (1560 1621), John Fabricius (1587 1615), who published his observations in June, 1611, or before Galileo, and the Jesuit father Christopher Scheiner (1575 1650), all of them pioneer observers with the telescope. End of section 11. Section 12 of the Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by K. Hand. The Science History of the Universe, Volume 1, edited by Francis Rolt-Wheeler. Astronomy. Chapter 9, The Sun, Part 2. Before sunspots were clearly observed with the telescope, it was assumed that they were due to the transit of Mercury. Even Father Scheiner, after his telescopic studies, suggested that the spots might be small planets revolving around the sun and appearing as dark objects whenever they passed between the sun and the observer. It was recognized, however, that the spots appeared to move across the face of the sun from the eastern to the western side, or roughly from left to right. Father Scheiner's view was also held by Jean Tarde, canon of Sarlat, by Father Malpertius, a Belgian Jesuit, and later by William Gascoigne, the inventor of the micrometer. Galileo, however, advanced a cloud theory, while Simon Marius, astronomer and physician to the brother Margraves of Brandenburg, proposed the ingenious slag theory, according to which the dark spots were the cindery refuse of a great solar conflagration, and occasionally expelled in the form of comets, which afterward blazed up with renewed vigor. Galileo, in a controversy with Father Scheiner, proved him wrong in his planetary theory, while the occurrence of the comets in 1618 won supporters for the theory of Marius. Galileo also ascertained the rotation of the sun in a period of between 25 and 26 days, as well as the general zone of the sunspots. The next important contribution to sunspot theory came from Derham, whose observations were made during the years 1703 to 1711. He believed that the spots on the sun were caused by the action of some new volcano, whose smoke and other opacious matter produced the spots. As they decayed, they became half shadows encircling the darker portions, and finally became bright spots. Lalande, the celebrated French astronomer, believed that the spots were rocky elevations, about which the penumbra represented shoals or sand banks, while around flowed enormous oceans. Lalande's explanation, as well as that of Derham, was clearly based upon terrestrial analogies, which were employed with considerable frequency by early astronomers. In 1769, Alexander Wilson of Glasgow (1714 to 1786), examining the large sunspot visible that year, noted that as the sun's rotation carries a spot across its disk, there was a change in its appearance, and that the same effect of perspective was produced as if it were a saucer-shaped depression, the bottom forming the umbra or central black spot, and the sloping sides the penumbra or surrounding portion of half shadow. The penumbra appeared narrowest on the side nearest the center of the sun, and widest on the part nearest the edge. Hence Wilson assumed that the great and stupendous body of the sun is made up of two kinds of matter, very different in their qualities, that by far their greater part is solid and dark, and that this immense and dark globe is encompassed by a thin covering of that resplendent substance from which the sun would seem to derive the whole of his vivifying heat and energy. Wilson went on to explain that the excavation of spots might be occasioned by the working of some sort of elastic vapor which is generated within the dark globe, and that the luminous material, which was more or less fluid, was acted upon by and tended to throw down and cover the nucleus. Sir William Herschel devoted considerable attention to the sun, and observing the variation in the sunspots, reached the conclusion in 1801 that it indicated a certain variability in the total amount of solar radiation, which he assumed might have some connection with terrestrial phenomena, especially the weather. He endeavored first in 1801 to trace connection between the price of wheat, naturally influenced by the effect of weather on the crops, and the occurrence of sunspots, claiming that when the latter were scarce there was a diminished solar activity, which caused colder weather, with obvious results. Ingenious as this theory was, there were not sufficient substantiating meteorological data. It finds, however, a counterpart in modern studies of the sun's heat, not necessarily connected exclusively with sunspots, however, whereby it is hoped to establish some useful knowledge of the relation between the amount of heat radiated from the sun and weather conditions on our earth. Herschel's observations of the sun and sunspots were continued by his son, Sir John Herschel, at the Cape of Good Hope, 1836 to 1837. John Herschel assumed that their motion was due to fluid circulations similar to those producing the trade and anti-trade winds on the Earth. The spots, in this view of the subject, he said, would come to be assimilated to those regions on Earth's surface where for the moment hurricanes and tornadoes prevail, the upper stratum being temporarily carried downward, displacing by its impetus the two strata of luminous matter beneath, the upper of course to a greater extent than the lower, and thus wholly or partially denuding the opaque surface of the Sun below. Such observation of sunspots, made with considerable thoroughness by the astronomers mentioned, as well as numerous others, did not establish any regularity in their appearance or effacement. It remained for Heinrich Schwab (1790 1875) at Dessau to announce in 1843 that the sunspot phenomenon reached a maximum probability in a decennial period. This announcement, although coming as it did after a patient study of the Sun, attracted no particular attention until a series of sunspot statistics were published in Humboldt's Cosmos. Then the correctness of Schwab's observations and deductions was apparent to all. When compared by Dr. John Lamont and Sir Edward Sabine with various periodical magnetic disturbances, it was found that the two cycles of changes agreed with extraordinary exactness. It was a remarkable coincidence that the observations of a number of investigators were in complete harmony. A study of sunspot records established the decennial period more correctly at 11.11 years. Thus commenced a recognition that magnetic disturbances on the Earth were related in some way to sunspot phenomena. For many years no direct connection could be established, although various theories were forthcoming. Likewise, further attempts were made to identify the variations of sunspots with meteorological phenomena, but without success, until Wolf in 1859, by an examination of the Zurich Chronicles (1000 to 1800 A.D.), found data which established occurrences of the aurora borealis to be correlated with a disturbed condition of the Sun. From this time on, the influence of the Sun on terrestrial conditions assumed new importance. The beautiful phenomenon of the aurora, which consists of a glow in the sky about the north and south poles, had been observed for ages, but the first scientific connection of importance recorded was in 1716, when Halley stated that the northern lights were due to magnetic effluvia. In 1741 Hiorter at Upsala observed that they produced an agitation of the magnetic needle. This connection was further demonstrated by Arago (1819), so that by the middle of the 19th century the connection of the aurora with the Sun, and in turn with terrestrial magnetism, was as evident as it was insufficiently explained. The first result of modern study of the sunspots was to put an end to the old notion that there was a dark and cold interior of the Sun, and that the sunspots were merely rents in the brilliant cloud covering through which the interior portion could be seen. The late Professor S. P. Langley, one of the most active of the modern students of the Sun and its surface, thought that the filaments, which taken together constitute the penumbra, were everywhere present on the surface. Professor Hale states, he regarded them as resembling the stalks of a wheat field seen on end in the undisturbed photosphere, and revealing more of their true characteristics in the penumbra, where they are bent over and drawn out toward the central part of the spot. Langley believed that we are observing clouds of luminous vapors rising from the Sun's interior, the seats of convection currents which bring to the surface the immense supplies of heat radiated by the Sun into space. Separating these luminous columns are darker regions, characterized by a lower degree of radiation. The minute details can be recorded only with the greatest difficulty. Under ordinary atmospheric conditions the solar image is not seen as a sharp and well-defined object, but its details are continually blurred by the effect of irregularly heated currents in our atmosphere. Even under the best conditions the moments of very sharp definition are few, and the greatest patience and perseverance are required on the part of an observer who would record his impressions of the solar structure. At the best, drawings based upon visual observations must be unsatisfactory, since even the skilled hands of Langley could not secure the perfect precision which is so desirable. It accordingly might be hoped that here, as in other departments of solar research, photography would afford the necessary means of securing results unattainable by the eye. Unfortunately, however, this hope has only been partially realized. The influence of sunspots is not confined to magnetic and electrical phenomena. The researches of Koppen, which have been confirmed by Newcomb, show that the average temperature of the Earth, determined by the combination of a great number of thermometric observations made at several stations, indicated a fluctuation of 0.3 degrees to 0.7 degrees Celsius during the 11-year sunspot period. In other words, the temperature of the Earth's atmosphere indicates small fluctuations which correspond with the sunspot period, thus indicating that the solar heat radiation varies with the number of the sunspots. The mean temperature of the Earth is greatest at the time of minimum sunspots and lowest at the time of maximum sunspots. Hence the determination of the amount of heat radiated by the sun at various times, especially at sunspot maxima and minima, is a matter of considerable terrestrial importance. The study of the sunspots, carried on by Professor Hale with the spectroheliograph and other apparatus, including special red sensitive plates of considerable speed, reached an interesting stage in 1908 when it was demonstrated that sunspots are centers of attraction which draw toward them the hydrogen of the solar atmosphere. Subsequently it was found that these spots are the seats of great cyclones, in which cool hydrogen gas is set whirling and is sucked down in the great maelstrom of the sun, rushing into the center of the spot at a rate of about 60 miles a second. Consequently, the spots are the center of great solar disturbances which are of an electromagnetic nature. According to the modern electronic theory of matter and electricity, electrons, or minute particles of matter, in their terrific cyclonic velocity, produce magnetic lines of force. It was found by Professor Zeeman that when light is passed through a strong magnetic field, the lines of the spectrum are subdivided and appear double. This Zeeman effect Professor Hale has found in the spectrum of the sunspots. If one looks at the center of a spot, the light travels in the direction of the axis of the whirl or cyclone, while in viewing a spot at the edge of the sun, the direction is at right angles to the axis and is manifested accordingly in the spectrum. This theory has been thoroughly confirmed, so that today it is known that sunspots are magnetic fields of great intensity. The important discoveries made by Professor Hale and his associates may thus be summarized as follows. First, that the spots are cooler than the surrounding region. Second, that they are centers of violent cyclones. And third, that they are magnetic fields of great intensity. In addition to the sunspots, the photosphere includes other interesting features, notable among which are the faculae, little torches, so named by Father Scheiner. These bright globular objects, besides the sunspots, are the only other phenomena of the sun's surface visible by direct observation. Schroeder showed that the faculae are heaped up ridges of the disturbed photospheric matter. Secchi and Young assumed that the faculae are the result of violent eruptive action of the sunspots, but it remained for the spectroheliograph to give a clear idea of their nature. Professor Hale states that they are usually most numerous in the vicinity of sunspots, and near the sun's limb they are sometimes very conspicuous brilliant objects covering large areas. Near the center of the sun, however, they are practically invisible, though faint traces of them can sometimes be made out on photographs taken with suitable exposure. This increase of brightness toward the sun's limb is assumed to be due to the elevation of the faculae above the photospheric level and their escape from a considerable part of that absorption which so materially reduces the brightness of the photosphere. Rising above the denser part of the absorbing veil and thus suffering but little diminution of light, they appear near the sun's limb as bright objects on a less luminous background. The chief difference of the faculae from the rest of the photosphere lies in their greater altitude, as photographs have shown that they may be resolved into granular elements similar to those constituting the photosphere. But they are the regions from which immense masses of vapors rise to the solar surface, and for that reason are important in the solar mechanism. Near the edge of the sun their summits lie above the lower and denser part of that absorbing atmosphere which so greatly reduces the sun's light near the limb, and in this region the faculae may be seen visually. At times they may be traced to considerable distances from the limb, but as a rule they are inconspicuous or wholly invisible toward the central part of the solar disk. The Kenwood experiments had shown that the calcium vapor coincides closely in form and position with the faculae, and hence the calcium clouds were long spoken of under this name. In the new work at the Yerkes Observatory, the differences between the calcium clouds and the underlying faculae became so marked that a distinctive name for the vaporous clouds appeared necessary. They were therefore designated flocculi, a name chosen without reference to their particular nature, but suggested by the flocculent appearance of the photographs. With the spectroheliograph, Professor Hale relates, it was at once found possible to record the forms, not only of the brilliant clouds of calcium vapor associated with the faculae and occurring in the vicinity of the sun spots, but also of a reticulated structure extending over the entire surface of the Sun. From a systematic study of spectroheliograph negatives, in the course of which the heliographic latitude and longitude of the calcium clouds, or flocculi, in many parts of the Sun's disk were measured from day to day by Fox, a new determination of the rate of the solar rotation in various latitudes has been made. This shows that the calcium flocculi, like the sunspots, complete a rotation in much shorter time at the solar equator than at points nearer the poles. In other words, the Sun does not rotate as a solid body would do, but rather like a ball of vapor, subject to laws which are not yet understood. End of section 12.
Section 13 of the Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Edward Labonte. The Science History of the Universe, Volume 1, edited by Francis Rolt-Wheeler, Astronomy, Chapter 10, The Sun, 2, The Reversing Layer, the Chromosphere and Corona, Radiation Pressure and Solar Energy, Part 1. The so-called reversing layer was discovered by the late Professor Charles A. Young during the eclipse of December 22, 1870, on which occasion he placed the spectroscope with its slit tangential to the Sun's limb so that it ran along a shallow bed of incandescent vapors. When the Moon reduced the size of the crescent of the Sun, the dark lines of the spectrum and the spectrum itself gradually faded away until all at once, as suddenly as a bursting rocket shoots out its stars, the whole field of view was covered by bright lines more numerous than one could count. This phenomenon lasted about 2 seconds and gave the impression of a distinct reversal of the Fraunhofer spectrum, showing bright lines for dark in every case. That such a reversing layer should exist was demanded by Kirchhoff's